All right, good morning, everyone. Thanks for patiently waiting as we work through all of our technical difficulties. I'm sure we've all had these on a daily basis. It's the funny thing about technology, when you need it to work, it won't. So anyway, welcome to our first in-person event in probably over 2.5 years for the OpCert program. My name is Ebony Roan. I am taking over duties for Noah Adams, which many of you are very familiar with. So I'm your new OpCert coordinator for the drinking water department. Speaking of just drinking water, we have quite a few things happening over the next year for the OpCert program, along with website updates and more trainings, more relevant trainings for operators, not just rule review. We're bringing in 2 more OpCert program coordinators for surface water, ground or wastewater for anyone who's specific in those certifications. We'll be having more events, not just in Phoenix, but we're also trying to reach out to smaller systems in the north and in the south, Tucson and Flagstaff region. Basic math courses, we want those here. We want them, want everyone just to leave. We want to be a resource pretty much. ADQ wants to be a main resource. So without further ado, thank you for coming to the All About Valves and Pipes events. We have 3 vendors today with us. We have CPM Pipelines, we have Arcadis, and we also have Hydra-Stop. We're going to start today with CPM's Pipeline, presented by Chris McDonald. Please come up, Chris, and the mic is yours. Just a little housekeeping rules. Please keep the questions to the end of the presentation. If you have anything further for Chris after the event, please reach and get in contact with him during our lunch hour or afterwards, but we'll also have his email and contact information on our webpage if you need it, or if you can email the OpCert program, we'll also provide that for you as well. All right. Thank you, everyone.
All right, thank you. So it's good to be back in person. I mean, we've, my company, CPM Pipelines, we've been scaling nationally for the past probably year or so. So all throughout this whole, kind of shutdown experience and changing of doing business, we've kind of continued on doing things the same as we always have. But locally here, it's been nice to be able to get back out and see people and doors are open again. So I appreciate that ADEQ asked me to come and speak and get a chance to get back in front of a bunch of people, meet some new people, maybe see some people I haven't seen for a while. So I've got a lot of information to cover. We're going to change things up a little bit, and I'm going to probably talk for as close to the 2 hours as I can, leading right up to 11, focusing on pressure pipe inspections and pressure pipe rehabilitation options. So that's what we specialize in. We've got a lot of really unique technologies. I think our tagline, trusted technologies, innovative solutions. So a lot of this stuff has been around for a long time. In the water industry, a lot of these things are typically pretty slow to get adopted. But over the last 10 years, we've done a lot of this type of work all throughout the United States. And hopefully I can share some things with you guys, maybe talk a little bit about access to some of these different technologies that may have seemed out of reach if you're a small utility, for example. So just to kind of get an idea of who's here in the room, obviously I think we're going to have some people online as well. But who here would consider themselves being from like a smaller utility, say, I don't know, less than 10,000 connections? Okay, and then how about like medium-sized utilities? I know I saw some Avondale guys. I'd consider them a pretty good-sized utility. Where's everybody else from? Like, what size utilities are you guys working at? Don't everybody speak up at once. I know she said there were no questions till the end, but I might ask you some questions. So. Okay, so we got the biggest cities in the valley, and we got some of the smaller. We're at? Okay, so good. So we got some of the larger utilities in the state and some of the smaller utilities in the state. So the like I said, the options we're going to talk about, that I'm going to talk about today, specifically related to like pipeline inspection. On the gravity side, the other question is, how many people are on the sewer side? How many on the water side? And how many do both? Okay, so we got a little bit of everything. So if you think about pipeline inspections, if you've been on the gravity sewer side, how long have those inspection programs been in place? And the technologies that are being used been in place? Probably since the 70s. You know, you saw some of the first CCTV cameras come out, some of the different cleaning systems come out for sewer systems as some of the legislation got passed in the 70s. So I was with a pretty good sized utility, a rather large utility actually in Southern California, probably 3 months ago. And they were really excited because they got their first camera truck. So, you know, I'm the one that's going to make the obvious comment. I'm like, you know, I'd be really excited too if I got some 1970s technology in 2022. I was just kind of giving him a hard time. But, you know, that stuff's been around for a long, long time. Now, there's been a lot of advances on the gravity sewer side. So, you know, there's high speed like panorama cameras. There's things you can run through the systems really quickly, go back and code. There's artificial intelligence type coding now that's out there. There's a lot of different companies that are offering different things to do prioritizations related to your pipeline systems. Most of them started on the gravity sewer side. So who in the room has some sort of program around like your CMOM with your gravity sewer side that does like inspections and rehab and camera work? Everybody? Yeah. How many of you have those similar programs for sewer force mains or water mains? Nobody? Yeah. Yep. And Phoenix, for example, they've done a great job. They've focused, a lot of the cities over the years have focused on, like on the pressure pipe side at least, pre-stressed concrete cylinder pipe inventories. So the type of technology that's out there and the types of pipes that they were seeing huge critical catastrophic failures 20, 25 years ago, a lot of those were PCCP pipes for a lot of different reasons. So I won't go into all those reasons today. But so the technology that was out there was basically the electromagnetics that was out at the time was kind of developed around those types of inspections. So a lot of big utilities around the country, Phoenix, Tucson Water, WSSC back east, you know, Vegas Valley Water District, a lot of different places were looking at those big, large diameter pipe inventories using the available technologies. Well, so most of the time when people saw that stuff, they kind of didn't pay a lot of attention to it because they either didn't have those same inventories, so it really didn't apply to them, or they didn't think they were a large enough utility to be able to take advantage of that type of technology. So what's changed though in the last 25 years is there's a lot of different technologies out there that are available. The price has come down considerably, and it's putting a lot of this stuff within reach to most utilities if you want to start working through and developing a program. I don't know if there's a clicker. Let's see. I'm just going to skip some of the stuff about us because it doesn't really matter. But so, and so there's different types of tools and technologies out there that you can use to do these different types of inspections on pressure pipes that aren't necessarily the same tools and equipment that you would see or use on a gravity sewer system. Okay. So, and that's really what my company is focused on, is trying to evaluate, investigate, vet a lot of these new technologies. And then eventually we were able to find some technologies out of the Netherlands and some different places that we've been able to bring to the United States and then introduce nationally across the country. So, and this has all happened over really the past like 2.5 years. We've been able to pull this stuff together. So I've been traveling all over the country since January, basically. This is the first time, and I live here in Mesa. So this is the first time I've really spent more than about a week in the Valley since January, and I've been back since the end of the WEFTech conference. So it's good to be back here, get to share some of this stuff with you guys, kind of show you what's developing on the water side and the pressure pipe side versus the gravity sewer side that you guys have seen, and it's kind of become pretty mature. You know, most of that stuff's pretty mature. There's some new stuff, laser and some different things that are relatively new. And they're always trying to come up with new stuff, but this stuff that we're going to talk about is really not new, but new to the United States and to a lot of the clients that we're working with. So, you know, and this is some of the stuff with the conveyance system. So we participate in some of this and do a little bit of it with different clients, but we really focus on the pressure side, but I at least wanted to just drop this in there. You know, manhole systems, rehabilitation systems, there's lots of new stuff with all these different types of things. So if you're still doing some of the age-old stuff, like for example with manholes, if you're still using epoxy on everything, there's a lot of different cost-effective solutions out there. You know, there's a place for those types of technologies, but there's a lot of new things out there that are very cost-effective. They're long-term solutions. They'll go 50 plus years, 50 to 75-year design life on some of this stuff. So if you've kind of gotten into this habit of going back and redoing the same things every 5, 6, 7 years, there's some better things out there. And if not that we do some of it, but I can definitely refer you to people who have a lot of this new stuff because we see it at different conferences. You know, we participate in probably 10 different national conferences throughout the year and presented a lot of them and exhibited a lot of them and networked a lot of them. So we're always finding lots of different things that are new. So this is kind of my agenda for today. And I'm terrible with slideshows, just FYI. I don't do well at just reading slides. So they're just kind of there for you guys to read if you want. I probably won't read them. But where do we start? If you're looking at pipeline pressure pipe inspections, you know, where do we start? How's it done? Why, where, when do you want to do inspections? Tools and technologies. I've got some rehab solutions I'm going to show you, and I'm going to show you a lot of deliverables. So I've tried to do a really good job over the past 2 or 3 years of learning the technologies we offer inside and out. If somebody asks for like a price on something, having that readily available and it's easy to come up with, deliverables so you can actually see what this equipment can do and what you get out of it. Because a lot of times we'll sell you the technology and it's like, well, what's the report look like? What's the deliverable look like? Well, we really don't have a whole lot to show you. Well, it's like, you need to see what that stuff looks like, right? Okay, so these are some of the different inspection like tools and technologies that are out there, and I'm going to cover a lot of this stuff with what we go through today. A lot of ultrasonic thickness testing. Initially, ultrasonic thickness testing was primarily focused on our ultrasound, so it's all sound wave based, and it was pretty much focused on metallic pipes. So now they've come up with ways you can inspect asbestos cement pipes using ultrasound technology, PVC pipes. Like if somebody asked me 2 years ago, how do I inspect a PVC pipe that I'm having trouble with? I would have shrugged my shoulders and I would say, I don't know. Yeah, because there really wasn't a way to do it because of how PVC pipes fail. So metallic pipes and looking at pipe wall thickness or remaining wall thickness, that's easy because everybody understands metallic pipes. You know, they corrode from a dozen different reasons. You know, stray current, hot soils. So there's a lot of things that cause metallic pipes to corrode. That's what the whole ASCE Pipelines Conference is really built around, is pipeline and corrosion. So nobody really had any ways to look at any of these other materials. But if you look at inventories right now, if you look at inventories across the country, so Utah State did their last report back in 2018, and it was a follow-up from the report they did in 2012. That report says like ductile iron pipe and PVC pipe inventories are about neck and neck now throughout the country. Different parts of the country have larger inventories. So if you go back east, you see a lot more ductile and cast. As you come west and throughout Texas, you see a lot more PVC pipes, right? And out here, you see a lot of asbestos cement because that's all that was put in for decades. So California, Nevada, Arizona, you see a lot of asbestos cement pipe. And that's another pipe type that there weren't really a lot of options on how you could inspect it. So has anybody ever done inspections on asbestos cement pipes? No? How about PVC pipes? No? Metallic pipes? Taking a look, seeing corrosion, check wall thicknesses, any of that sort of stuff? Who's interested in developing programs so that you're not doing emergency repairs every other day? Anyone? Maybe? Okay, so and that's the whole idea. So that's kind of what the point to this is. But ultrasonic testing was initially really focused on metallic pipes and figuring out what the wall thicknesses are. And we actually use those on in conjunction with electromagnetic testing that I'll tell you about here in a minute. But we pair that up with like an electromagnetic bracelet probe because the type of data you get doing an electromagnetic inspection is relative. So unless you can calibrate it to the specific piece of pipe that you're trying to inspect, you have to validate the data with another instrument to tell you what the actual thickness is. And I'll explain this a little further later. So you kind of use the two in conjunction, and I'll tell you how that works. We have pipe scanners that are ultrasonic based that you can use on all types of materials. CCTV and swimming inspection technologies are out there. Pipe wall thickness imaging, GIS. Who's got a good GIS? Or who doesn't? That's probably a better question. Who doesn't have a real good, accurate GIS system? Everybody does? Wow. Usually if I have two people in the room, at least one of them will say they don't. You don't have one? Yeah. So, but that becomes critical. That causes breaks and failures and unexpected strikes and things like that if your records aren't accurate. So there's ways to collect that information at the same time you're doing pipe inspections. Air valve assessments, maintenance, and repairs. I bet when I started doing air valve type stuff, probably 20 plus years ago, I'd go out and we'd start popping lids and looking in vaults, right? Or go to the lift station and see what kind of air valve they've got. And Dane at Arcadis is going to talk a bunch about air valves later. But usually the way people fixed them when they started leaking or something was wrong was they turned the shutoff valve off underneath them. And we'd go out and look at them and we're like, well, what's wrong with the valve? They're like, I don't know, and I don't know how to fix it, so we just shut it off. And it's like, you realize those were put in there for a reason, and all those reasons Dane's going to get into, but that was the most common thing we saw all the time. So we actually started doing a lot of inspection, assessments, and repairs on air valves because nobody knew really what to do with them or how they work. Now, there's been a lot of that change over the last few years, and we've, especially here locally, we've got some good reps that are doing a pretty good job of talking to people and educating people on it. But it was something simple to repair and inspect and assess to kind of get in the door and get some things started with clients. I was even in Prescott yesterday, and the one comment that came up during the 2-hour meeting with them was, yeah, we've got 16 air valves on this old Ameren pipe. We have no idea what shape they're in, and maybe that'd be a good place to start. I said that'd be a great place to start doing some inspection work. So then Aquarius inline inspection tools, that's a UT-based inline inspection tool I'm going to tell you a lot about and show you a bunch of reporting. I'm also going to talk about some of the other options out there that other companies use. Like I said, air pocket locating, surveys, leak detection, things like that are good inspection alternatives. And then again, you guys are all probably familiar with the sewer assessment inspection programs, but not so much on the water side. So. All right, so, and I don't know if you guys read any of these reports. We're really active with AZ Water. We're very active with the National AWWA, with the Water Main Condition Assessment Committee. We're rewriting the M77 manual currently. If you're interested in developing a program or any of the stuff I talk about today, and you haven't even started, a really good starting point is that M77 manual of practice that the Water Main Condition Assessment Committee put out like in 2019. We're already revising it and updating it because the technologies are changing so quickly. So actually that we've added a chapter for ultrasonic inline inspection that's going to be part of the next edition to come out that'll probably be out in about 2 years. So there's lots of stuff going on currently, and I think that we've added about 3 other chapters. And if you're interested in participating in stuff like that, we're happy to have you, and you don't even have to be an AWWA member to participate because we're looking for industry experts and just people that are familiar with these systems. So, but a lot of this stuff comes from those types of studies like the Utah study, 240,000 main breaks annually. I don't think that's even close to what it really is. Water loss, SSOs, repair costs into probably hundreds of billions of dollars. Water loss, non-revenue water is becoming a big thing. There's a lot of technologies out there for helping with that, whether it be pressure transducer based stuff or acoustic leak detection stuff or modeling type stuff. So there's lots of new things out there in that side of the business. Obviously drought. We're getting ready to hit the next tier, I think, with the drought contingency plans and things going on with Lake Mead. So that's always getting updated and changed. So this is becoming a more important issue all the time. For example, when we're doing pipe inspections in California even, in the past, they would simply shut a main down, dewater it, pump it out, and then refill it, repressurize it, retest it, rechlorinate it. Well, now that's going to become less and less of an option as water scarcity becomes worse. So finding tools that you can use with the mains in service without having to dewater, a lot of that stuff's going to start making an impact as we go forward. But the triple bottom line stuff, you guys have probably heard that before, the economic side, the social side, the environmental impact. So having a program in place, and like I said, you don't have to start with a huge budget, but just put a budget in place, start doing some planning, come up with a plan and a way to execute it, because the impacts that you're having on local businesses in the area, neighborhoods, if you have sewer overflows, force main breaks, things like that, they're very expensive, for a lot of different reasons besides just what it costs to fix the pipe. So we always look at starting with like a phased-based approach. And again, you can kind of start with like really high-level survey type stuff, whether it be going out and setting out loggers to survey your entire system for leaks, right? If you've got a lot of AC pipe, a lot of metallic pipe, that's a good starting point. But what you're trying to do is come up with a prioritization schedule to figure out where you want to look closer at the pipelines in your system. So you don't, and there's easy ways to do it. I mean, you can look at age, but age isn't necessarily the right way to start, because just because a pipe's older doesn't mean it's necessarily in worse condition than a newer pipe. So there's a lot of different factors that kind of play into that prioritization side. So are you being proactive, reactive, or even now you can take that a step further and be predictive? So are you trying to do inspections and figure out what's going on? Are you waiting for things to break and you're just reacting to them? Or if you take it to the next step, and I'll show you how this can work, you can actually take the data you get today doing an inspection and then use that information to predict when and where that pipe's going to break in the future. So that's what's key to this whole thing, because if you know that, it's a lot easier to manage your systems, right? If you know when and where the pipes are going to break, it's like, all right, well, we know when we have to fix this. Otherwise, you're just kind of flying blind, which is what a lot of utilities are doing right now. So it's just changing mindsets. Like I said, reactive, you monitor run to failure. Proactive, understand the condition, come up with RUL, which is remaining useful life. So you'll see that acronym a few times. There's different modeling things that can be incorporated into this stuff, desktop stuff to start with. And most recently, and like Dane and the group at Arcadis, that's what they do. They're experts at this stuff. So getting in on the front end, doing the analysis, figuring out where you want to prioritize and where you want to get the tools out into the pipes. And we've done a lot of projects with them where we come out and do the actual inspections. They do a lot of the front end work, a lot of the back end work, reporting, analysis, stuff like that. So why is it necessary? We've all seen these, I think, right? The geysers. Who was I talking? Oh, well, I was up in Prescott yesterday. They said, yeah, we don't like seeing it. I can't remember where he said, but there's some place they keep having a PVC main pop and they keep having 100-foot geysers. It's like, yeah, those are easy to find. We just wait for the geyser to come up in the air. So usually on a phase-based approach, you're starting with the risk analysis. So we're looking at likelihood and consequence. We're coming up with those scores, putting them on a risk curve like you see down at the bottom. And, consequence, what happens if the pipe fails, like how catastrophic is it going to be? Likelihood is the condition assessment part of it. So we provide, and these tools we're going to talk about provide that condition assessment or the likelihood part. And then when you take it further to the predictive nature, it really takes that out, and you can take it out like that portion of it out like 100 years. So we're prioritizing the system assets and liabilities, trying to determine what the risk is, and then evaluating the different technologies with a mission statement in mind. So how many of you guys have been involved in like trying to solicit for a technology, like you're trying to do some kind of assessment and you put a solicitation out trying to get some proposals in to evaluate to decide what you're going to do? Has anybody been involved in anything like that? What we see all the time, so if you think about these types of projects and these types of programs, you've really got three very specific pieces to it. So you've got a consulting component that companies like Arcadis focus on. And there's lots of different pieces in this puzzle that they're really, really good at, and the different consulting companies are good at. You've generally got some sort of contractor component involved, and then you've got a technology component. So my company, we focus on the different technologies, whether they're ones we provide or someone else, but there's two other clear pieces to that puzzle. And what I've seen is when these things get put out for proposal, there was one specifically in California that never ended up getting done because of how this thing got put on the street for proposals to come back. And what they did, they had stacks and stacks and stacks of as-built drawings, studies they'd done in the past, plan sheets, profiles, environmental information, because the pipes were in an environmentally sensitive area that if you dug anything up, there was some sort of dodo bird that you had to work for 100 years to make sure he wasn't disturbed. All that stuff they put into this proposal, but the one thing they didn't include was what they were trying to do. I think they put what they were trying to do by just saying that we want the pipe assessed or inspected. But that really doesn't tell somebody like us or a contractor or a consultant, like, what are you trying to accomplish? You know, are you trying to decide when and where it needs to be rehabilitated? Are you trying to make a go, no-go decision on replacement of the entire main? Are you trying to do surgical spot repairs? You know, what are you trying to get out of this inspection? So that's, if nothing else, if you ever try to put something like this on the street to figure out the condition of your mains, always make sure that you include what your mission statement or your goal is associated with whatever that work is, because that'll help people provide you the information that you need to make a decision. And don't always lean on the same people for bringing you technology information, because it changes so quickly. Don't be afraid to step out and ask somebody. You know, you guys are, I'm not the brightest person around, but I'm smart enough to go out and find this stuff and know the right questions to ask and evaluate the different technologies and figure out what's going to work and what's not going to work. And trust me, I found a lot more stuff over the years that didn't work than worked. But now we've got all the things that we figured out worked that we can provide our clients, right? So just keep that in mind with the mission statement and the goals. The other thing that's real important too, don't forget about the cost to replace or rehab something when you're going through these exercises. Because if you're looking at like a 4-inch main, for example, a lot of times it's cheaper and less expensive for us just to pull a rehab liner through a 4-inch main than go through some expensive inspection process. You know, so just really know what you're trying to accomplish and take all these different things into consideration when you're doing your planning. So these are just some of the different failure mechanisms that you see with different types of pipes. Internal issues, operating pressures, transient issues. You guys monitor for like transient events or surge pressures in your system? If you do, have you ever seen a failure coincide with a surge event? Something else that the air valve discussion we'll talk about, because that's part of the reason those valves are in place, and you can have a lot of surges take place because of the air being in your system and compressing and then kind of breaking loose around a bend or a corner, and that causes all kinds of havoc on your system. Hydrogen sulfide gas, like on the sewer side, just wrecks metallic mains. When that combines with oxygen in the air, creates sulfuric acid, eats away your linings, eats away your coatings, eats away the interior of your metallic pipes. Joint defects, corrosion, tuberculation, debris inside the pipe are all things people are looking at and cause problems. Externally, you can have corrosive soils, stray currents, subsidence, a lot of third-party damage, a lot of adjacent utility stuff. And the one thing I don't have on here, which I don't know why, but construction-related issues. If I look at all the pipeline inspections we've done for the past 10 or 15 years and all the things we've seen, I'd say 95% of premature pipeline failures are construction-related problems. And again, that's, we had a meeting with Tempe not long ago, and one of the guys from Tempe, one of the engineers at Tempe had actually said, you know, years ago we had, as part of our new construction, a program in place and it wasn't when he was at Tempe, it was somewhere else. But he said we had a program in place where before we would start a pipeline installation project, we would make sure that the manufacturer of the pipe came out and talked to the pipe crews so they knew exactly how to install pipe. Seems silly if you think about it, but what's not silly is I can pretty much walk onto any job site that's putting PVC pipe in the ground and ask every single person in there putting it in what the 2 marks on the end of the pipe are, and they don't even know. And then the next question is, well, how far do you push it into the belt before you stop? Well, till it stops. And that is not the right answer. That's why we have PVC pipes all over Arizona failing after 10, 15, 20 years, is because it wasn't put in right. If it's put in right, it'll last 100 years. And there was a study actually done. If you're in Pima, you know who Lawrence Wynn is, that was at Tucson Water. He was an inspector. No? So he wrote an article, not to the satisfaction of management, because it was related to developer installs. So he was poking the developers. But in I think it was 2018 or 2019, the January or February journal, AWWA journal, they published this peer review article, and the article was basically about how they were allowing subdivision installations where they were longitudinally bending the pipe to avoid putting fittings in. Well, what he found, and the couple, and there's a lot of really good information in there, and any of these things I'm referencing, if you guys want more of these, to read these articles or get this information, I'm happy to send it to you. You just have to ask me. But what the most interesting graph in that article, or that peer-reviewed paper, it showed PVC pipe failures from 0 out to about 80, and then how many breaks per 100 miles of pipe, basically. So how that graph looked is from 0 to 10 years, it went up like this to where it maxed out at 0.1 breaks, I think, per 100 miles on PVC subdivision pipe installations. Then from there, it drops linearly, almost perfectly straight, down to 30 years, and at 30 years, it flatlines. So what's that tell you? All those failures are all installation related. So, and that's caused by, the other thing that's not mentioned up here, I've got joint defects, but stress in the pipe wall. So for metallic pipes, you're looking for corrosion. For PVC pipes, you're actually looking for stress that's being created in the pipe wall. So then you've got to figure out what's causing the stress in the wall. So if you guys have ever been in the field and dug up a pipe and went to cut it, what happens oftentimes if you've got a 45 offset going under something, and then it comes straight, comes back up and goes straight again. We see a lot of this because a lot of the rehab work we do is through 45 bends. So we'll cut it right up top where that bend straightens out again, about 8 to 10 feet away. We just did one last week out in Maricopa with Global Water on a rehab project. Has anybody done, like, made a cut in that type of location on a pipe? Do you know what happens 90% of the time when you do? If your pipe's lined up like this when you start, as soon as you get the saw almost all the way around it and finish your cut, it does this. So think about how much tension was on that pipe for however long it had been in the ground when you had that huge offset. We were off 6 inches, and it was ductile. It wasn't PVC, it was ductile. And when we cut it, it snapped, and we were off 6 inches when we were trying to line it all back up and put everything back together. And it happens all the time. And if you think about it, getting that pipe put in properly, so when you're making your ditch and you're dropping down 45 degrees and you're going under, you've got to get everything compacted and under the haunches of the pipe and get everything backfilled properly. But think about how hard that is as you're making that break, and now you're going down at an angle to keep everything packed in and compacted where it's supposed to, and how easy it would be just to not worry about it. But that's what causes all these pipes to fail and causes problems. So just a couple of other things that I didn't have on my list. So modeling, a lot of cities, a lot of places do modeling. It's a good starting point. You can take and add just basic information you can collect in the field every time you have a main break to your modeling system. There's pipe scanners that are out there. There's UT sensors, you know, they cost $1,000 a scan, and you can do them yourself. You can get sensors that cost $3,000, $4,000, $5,000. You can go out and spot check metallic pipes and just kind of see what the wall thicknesses are in the area. Start adding that to your model and just using that information that's readily available when you have a break to start improving your model and making it help you make some of these decisions in the future. So you can see if the pipe's operating as designed. Is there pressure in the volume consistent? Are your pumps pushing what you plan on your pumps pushing? Valve operation, variable pressures, ARV operations, all these things can be easily looked at. But potential locations of anomalies, deterioration, debris, tuberculation, you can start modeling a lot of this stuff and kind of have a pretty good guess where some of these things are going to happen. But what you can't find is where the actual air pockets are, where the actual debris is, where you have leaks, where you have material changes, where there's degradation in your system, if your XYZ mapping is correct or not correct in your GIS system. So, what we're trying to do is make sure you have the right tools, collect the right data to make the best decisions long term. And more importantly than making the right decisions, I make wrong decisions all the time. So we're all going to make mistakes. It's just how you handle those mistakes and making the necessary changes when those mistakes happen to improve upon what you were doing before and make it better, right? But you got to start somewhere and you got to do something. Or your budgets, if you look at the shortfall they're talking about with budgets in relation to infrastructure, like grade cards, like I don't know where the money's going to come from, I guess. And the thought is, well, they always figure it out, right? Well, what if one day they don't? What if one day there isn't enough money to fix that main break? Or what if there isn't enough money to make the improvements or repairs that are needed? Well, it's easy, I guess, to get the money. We just raise rates and we all pay more, right? So I don't know what happens when instead of gas going up to $7 a gallon, we see that same type of increase in our water system rates. But it's up to us to make sure we do our best to manage that and budget properly and utilize the money that's out there as best we can to keep a lot of these emergencies and different things from happening. Got to watch me. I'll get on a soapbox, start preaching. So desktop analysis, modeling, visual inspections, hydrostatic, ultrasonic, leak detection. There's a lot of there's a couple of different companies out there now that they can optimize where they put basic pressure sensors throughout your system and then model and use that pressure sensor data that they collect to tell you where you've got system problems, tell you where you might have a leak. So there's lots of different information that's relatively inexpensive to have done. There's also companies out there, anybody heard of a company called Fracta? So Fracta was basically, to drill it down and keep it simple, they were basically taking break history, pipe material, installation date, stuff like that, gathering all this information from as many utilities as they can around the country, running the analysis and kind of kicking a prioritization schedule out. And it wasn't that expensive. I mean, they charge like $35,000, $40,000, $50,000, I think, to run it the first time. And then you could have it ran again like every so many years, and it was less expensive once you did it the first time. But there's other companies out there like Suez right now that they'll run that stuff for you for free. It doesn't even cost anything. So there's things out there that are really useful, that are, I mean, as cost effective as you can find, because some of it's free. Water Research Foundation has some of this stuff free, starting with something like the M77 manual, that's $180 to help you start thinking through some of this stuff. So it doesn't take hundreds of millions of dollars to get started. So these are some of the different tools and technologies. We talked a little bit about modeling, desktop stuff. There's low resolution screening tools. So I would consider like leak detection equipment, inline inspection balls like you see on the left and the right here on the bottom are kind of low resolution screening tools. So you just get a couple of specific data points that you then kind of use to do other things with it. Or you can go to like a high resolution inline inspection tool, which would be like this tool, this tool, this tool, this tool. And I'll talk about each one of those a little bit, some more specific. And then there's validation tools that we use in conjunction with the survey tools to actually see what the problems are in those specific areas that the survey tools kind of point out to us. All right, we got to start out, I guess, with the 1970s tech. So, you know, there's lots of different companies, you know, out there, iBot, Q's, Aries, that offer simple CCTV systems. There's a company called Deep Trekker that they changed the name recently, but I can't remember what it's called. But it was Deep Trekker. Sam McDonald owned it. The first camera system we ever bought was from her. It was a simple crawler. It costs like, I think they only cost about $20,000 now. You're not going to get a lot of information when you're talking about like pressure pipes specifically using this tech, but you can see like broad areas of damage, construction damage, what you can't see. So if there's like coatings that have gone bad, you may or may not see it. In a water main, you could have alum or something all over the pipe walls and you can't see anything. In a sewer force main, if you've ever opened up a sewer force main, if it's not plastic, it's generally black on the inside and you can't see anything. So, and you can't clean them like you can a sewer system, right? So if you think about a gravity sewer system, you basically go down to the low manhole, you shoot everything up to the top of the upper manhole, and then you drag it all and pull it all back, and the water all comes back to you, right? Otherwise, those trucks don't work real well, especially you get the recyclers. I had somebody tell me, yeah, bring a recycler out, we can keep running on your force main. Well, he gets out there, and like after 20 minutes, he stops. I'm like, what are you doing? He goes, well, we're not getting any water back. I said, well, it's not a gravity sewer. I told you it's a force main. He's like, well, we can't get enough water to keep the recycler going. So he still had to keep going and filling up and getting water. But so you really have to think about this type of tech and what you're going to use it for if you want to put it in a pressure pipe. So there's some things that are useful, but there's some things that it's really not going to give you. Like, for example, if you were to open up a plastic PVC water main or force main that you're having problems with, if you've got a split that's already occurred, you'll see that, but that's not what you're looking for. You know that's going to surface in a week. You know, if it's already split, you want to figure out where it's going to split the next time. But you can't see stress in a PVC pipe wall with a camera. It's, you know, that's not. And if you've ever looked at like CCTV footage on a sewer even, unless you have something high definition, a lot of times if you're running straight, that main can be gradually turning. But if the camera's not high definition enough and you can't see far out ahead of you enough, you think you're going straight and you're turning the whole time. And you may be going this direction and you think you're still going this direction. So there's a lot of things you got to think about with these different technologies. So there's swimming stuff that you can put in your tanks. Who's ever used divers in a tank? What's your safety and your insurance people think about that? I bet they'd prefer this, right? So there's a lot of low cost, really effective ways to get in and inspect tanks. We've put these types of tools in 96-inch diameter pipes and swam them 1,500 feet down the pipe in 10 minutes to look at valves, whether they're open or closed, and found stuff that was supposed to be closed that was wide open. But these are again, pretty simple. You're not gonna get really high resolution data. You can at least get a look at something if you wanna see something. They can be outfitted with like grab arms and things. Like we've used stuff like this to go into a tank, and the cable that was connected to the elevation on the outside had fallen off, and we went down and grabbed it and pulled it out so they didn't have to take the tank down or send a person in. So there's a lot of useful things you can use these types of swimming ROV systems for, and they're out there. So these are your 3 different options really that are out there. I don't think Hydromax is even doing Nautilus anymore, so you can scratch that one off. But these are designed to pick up acoustic data primarily, like leak noises and air pocket noises. We use the, so this is an inspection ball that a company called Pure Technologies offers called Smart Ball. This is an Ingu ball that we use called Piper. The Piper inspection balls, the reason we use those for doing inline, so what you do is you basically remove like an air valve, for example, at your lift station. Shut the isolation valve, pull the air valve off, drop the ball into a launch tube, put the cover on it, open the valve back up with the force main running, It'll shoot the ball from the lift station all the way down to the outfall or the bar screen or whatever's at the other end. What we're using these for is to find air pockets. So we're mostly trying to find air pockets on metallic pipes or air pockets on asbestos cement pipes. Then once we find the air pockets, in theory, that's where you're going to have the worst degradation on the pipe. So once we find that, we'll go back with a validation tool, expose the locations where the air pockets are, and do a higher resolution inspection at just those 2 or 3 spots. But at the end of it, once you get that information, you have to be ready to make whatever decision you wanted to make based on 2 or 3 10-foot sections out of maybe 2, 3, 4, 5,000 feet of pipe, right? So just know that if you go down that path, and we've done these types of inspections with Dane and his guys at Arcadis, went back out with validation tools, and now we're talking with some of these clients we're working with these guys about going in and doing a full inline inspection because they got the data, it didn't look great. And they're like, well, now what? Well, we either make a decision with this or we get more information. And here's what it costs to get more information versus what it costs to fix it, or just make the decision to fix the whole thing. The Piper inspection balls, just to point out some of the things that are a little different, it's zero buoyant and it flows right down the center of the column of water. As long as water's moving, it'll stay centered in the column, so it kind of has a better chance of picking up the data we're looking for. Where the smart ball type technologies are in this foam core they put them in, and they roll along the bottom of the pipe, so the data is not as clear. In addition, we can use the Piper balls can be used to pick up pressure data, temperature data. They have accelerometers and gyroscopes on board, so you don't have to track them. You just pick up all the location information when you post-process the data. So it makes it a little bit easier on the field side when you're out in the field doing them. And this just shows the different sensors this has on it compared to the other tech where it's just acoustic. Now, here something that to come back to the leaks on water mains, right? Like PVC pipe. Can you hear leaks with this type of technology on PVC pipe? My answer is no, because that's not what causes PVC pipes to fail. It's the stress in the pipe wall that doesn't create a leak noise that can be picked up with an acoustic device, right? So we only use these for air pockets on force mains. A lot of clients over the years have used these for leak detection on water mains. And the pitch is, for the smart ball, not the Piper so much, the pitch is, you can pay us $200,000. We can put it in here. We can let it run. We have to shut off all these branch outlets. So we need your operations team out there for 40 hours, isolating valves and opening valves and closing valves and making sure valves aren't broke. Then we'll catch it 25 miles away and tell you where all your leaks are and charge you $200,000 or $300,000 to do this. You can also take transmission main correlators that hook up to the outside of the pipe to the fire hydrants, typically in your system with hydrophones on board. And one of my 2-3 man crews can go out for $4,000 or $5,000 a day, do 5 miles a day. So that same 25 miles, without your crews ever having to be out there and do anything, you can get leak detection performed in like 5 days for $20,000, $30,000 versus one shot. Maybe you got it, maybe you didn't. Could have data, could not have data when it comes out the other end. And what you definitely are going to have is a bill for about $200,000 or $300,000. So there's different ways to do these things. So just find somebody you trust that knows something about some of this stuff. Do some research, but there's lots of different options. So these are some of the different validation tools that you can do on the exterior of the pipe. The ultrasonic thickness gauges, we do a lot of this stuff. It's just a transducer that you couple to the pipe with like a gel. You just touch it, you get it set up and calibrated first to the type of material, and then that reflection, that sound wave is going to come off at a specific speed based on the material type, and it'll tell you exactly what the thickness is at those locations. The bracelet probe that's in the middle, this was a 18-inch force main we did for Sedona last year, I think. Ductile iron, this was an air pocket location. Okay, so this is like the next step. We found air pockets in just a few spots. Their crews went out and dug this one up. Sometimes they'll have a contractor get involved, exposed it, and then we basically take this bracelet, which is maybe hard to see way back there. I'll have some other pictures past this to show you. And it takes a little bit to set up. So everybody's like, well, how much pipe can you do a day? Well, we can do like 3 locations, 8 to 10 foot. Each location, really anything from about 8-inch diameter up to big diameter stuff, 72 or larger. But we get 10 inches a pass. So the bracelet's got a scan area of 10 inches. So we have to keep rotating it around the circumference of the pipe. But even if it's large diameter pipe, once we're set up and the pipe's marked, because you have to kind of mark everything out, run the bracelet, then it's real easy to rotate it, do the next scan, rotate it, do the next scan. Then once we find the defects, looking at the relative data, which when I say relative data, I mean a bunch of squiggly lines on a readout on my computer that we interpret to what the interruptions in the electromagnetic signal are. Then we go back at the worst spots we see and we verify the thickness with the UT sensor. So that's, like I was talking about earlier, that's how you kind of combine the different technologies to be able to locate the air pocket, do the electromagnetic scan, because that'll allow us to see both the exterior and the interior of the pipe. Then once we find defects, we can actually verify the thickness with the UT. So it's a process you kind of have to walk through. The electromagnetic broadband tester, it's similar to the bracelet probe, except you're just spot checking stuff. And then the newest piece of equipment that we have is the pipe scanner, which is at the bottom. So it looks like a big mouse. And these things can work on any type of material. They're ultrasound based. There's a couplant or a little coupling underneath it. And what you do is you hook it up to a water hose or a water source. The water couples the sensor to the pipe, and then you just press it down, the thing turns green, and you start walking it down the pipe as quick as you can. And you get about 1.5 inch wide path with absolute thickness data. So it works for asbestos cement pipe, it works for any metallic type pipes, and these are all things that you can hire a company to go do, or you can get these pieces of equipment in the hands of your field guys, and they can go out and collect this data every time you have a break open up. So again, same stuff I covered. This is a little bit better picture of the bracelet. Just real quickly, how this thing actually works. It's called electromagnetic through transmission. You have an exciter on one side, a detector on the other side, and on the front, you've got a set of 8 sensors that are called the absolute channels, and on the back, you've got 8 what they call differential channels. So what happens is when that signal, it's basically cycling through the pipe wall like this, and when it picks it up coming off the outside, the absolute channel picks up corrosion and broad areas of degradation on the outside of the pipe, and then the differential channel, based on time of flight and how long it takes that signal to come back and what the interruption looks like, picks up all the localized pitting and defects on the inside of the pipe. So this is just some other shots of the inspection balls from Ingu, so the Piper inspection balls. Again, this was a 30-inch pipe we did in Albuquerque, I think 1.5 years ago, force main, but we just removed the 4-inch air valve at the lift station, put our launch tube on, our valve on top of that, drop the ball, and then open the isolation valve up with the main running. It just drops in and shoots to this shot to the bar screen, which was great because it made it really easy to catch. We had to just stand at the bar screen at the plant. It comes up on the screen. You heard it hit the trough, like thunk, and then just start rolling down the trough, and all I had to do was grab it. It's like the easiest job we ever did. So this is why I'm terrible at slides. I talk about the slide before I even get to it. But 10-inch wide path, electromagnetic through transmission, 16 channels, 8 on the front, 8 on the back. But at the top, that's how we can convert the data to like a thermal image. So you can actually kind of visualize where the defects are and what they look like. So this is a little bit better shot of the pipe scanner technologies. Again, UT, linear path, metallic, PVC. I mean, we mostly use this for asbestos cement because the electromagnetics is more cost effective and the UT is more cost effective for the metallic stuff. But ultrasonic and really quick results. So these are, a lot of this reporting comes in HTML files. And like we would share a lot of this stuff, like if you had a consultant involved, partnered with us, we would send it to them. They would do their analysis and reporting. But this would show like the maximum thickness, the minimum thickness that was measured in that scan, and then what the averages are is in the middle. So, and if you, I've got another picture, I think, that shows scrolling over one of those data points, and it'll pull up all the specific details for each scan. This is a video that probably won't play, but return on investment on using these scanners is, and a lot of this stuff is typically less than a year. You can use and deploy these things yourselves a lot of times with a little bit of support and a little bit of training. You know, no health and safety risks when you're grabbing specimens, especially like on AC pipe. So if you had looked at AC pipe in the past, you really had to cut a sample out, send it to the lab. The lab would do finite element analysis. They do like crush tests sometimes. They'll do phenolphthalein tests. Well, a phenolphthalein is a typical dye test that you do for an asbestos cement pipe. And what you're doing is you're basically trying to see how much structural density. If you look at AC, a lot of times it looks and feels solid, but it's not, because of leaching that's occurred from either the product water inside the pipe or groundwater on the outside of the pipe, or H2S attack in this case of a force main. So it may look structural, but it's not. So it doesn't have any pressure capacity or hoop strength, or not as much as it did initially. So this will tell you exactly how much remaining structural density it has. So if the pipe wall was originally like 0.6 inches thick, we can tell you if it's got 0.6 inches still, or if it's like 0.2, because the UT can tell the difference in the density of the different types of materials as the material leaches out. So I've got a paper that was written on this that explains exactly how it works. And if you're interested in reading it, I'd be happy to send it to you. Oh, it does work. Maybe. Yeah, so you can see it running. It's pretty simple. And it's literally that easy. You just hit the button, collect the data, hit the button again to stop it. We upload it and validate it, or you would upload it and validate it right away, and it'll actually tell you if your scans are good or bad. So if you have to redo them, you'll know before you ever leave the site. This is just a zoomed in view of some of that same data. You've got the pipe type, diameter, stuff like that, OD, ID on the left side, and then the different scans, same spot here. Then you can also click to get additional information, like on this spot, and it gives you like a scatter graph that shows you all the data points instead of the summary. So these are the different high resolution inline inspection tools. So I'm probably, you know, this is going to take the next hour. Normally we'd have a break right now, so it's kind of hot in here. You guys want to take a quick 5-minute break before I jump back into this next hour, or you want me to just keep going? Is that good? Okay, let's do that. stuff. Is any of this information useful? Yeah? Okay, good. I like to think so, but it doesn't really matter what I think. It matters what you guys think. So, and we've been working on a lot of this stuff with the different like organizations. I'm involved with like different committees and things. It's trying to make a point to do outreach, talk to the guys running the systems, talk to the management at the systems, and find out what's needed and what everybody's looking for and what everybody wants. Because I think a lot of times as organizations, we just kind of pull from within our group, and we don't do a good job all the time of like reaching out and really asking the people that need the information what information they want. And that does a better job to help encourage participation at all different levels, as well as making sure we are providing the information on the things you guys are looking for. So, you know, I of course find this stuff all fascinating. I've spent the last 2 or 3 years really teaching and training the people on my team on how a lot of this stuff works. And as we get more and more into this over the years, and we start really diving into and digging into the past technologies that are out there, we're really, there's some that are really, really good, and there's some that are a little lackluster, to say the least. So we're excited to be able to bring some new stuff to the market. It's cost effective, the data is good, it allows you to figure out what's going on with all different types of pipes, not just specific types of pipes. And if you look at the tools that were out there 25, 30 years ago when this all first really began with big diameter critical catastrophic failures, you know, so some of the information that was available was pretty limited, and they were having to do a lot of like Monte Carlo simulations and different things to really try to come to some conclusions. So what's exciting now with some of these new tech on the left, with the ultrasound-based technologies that are out there and some of these new chapters being written as part of some of these committees, is the amount of data that you can get on your pipes that just really wasn't out there in the past. So the two technologies on the left, these are from a company called The Quaint out of the Netherlands, which is who we've been working with for about the past 2 years. This technology is one of the more current technologies from a company called Pure that's owned by Xylem, who a lot of you have probably heard of. And then this technology here is provided by a company called Pika out of Canada. And we've actually worked and done a lot of work with Pika over the years. And then we're actually partnered with the company that provides these technologies. The two technologies on the right are pretty much 100% focused on either multi-layer pipe, like a bar wrap, a PCCP, or metallic. So ductile, steel, and most of them are using electromagnetic data, either near field or remote field. And just to keep it simple, basically if you're using, they're creating a magnetic field inside the pipe that allows them to look at different features, whether it's deterioration or degradation across wire that would lead to an indication that they would say could be distress in the pipe, which I'm not convinced it really does that very well because of several factors. Or if they're looking at the steel can component, for example, in a multi-layer pipe. So that depends on how far the exciter and the detector are spaced apart is what means near field or remote field, and it's how the fields are created, the magnetic fields are created in the pipe, just to keep it super simple. So they both do a little bit different things. Now the sea snake technology, it's really good at getting you just really, really highly accurate, detailed information, but it's very expensive. So if you want to put this thing in like a 36-inch bar wrap pipe, they're going to have access ports about every 1,500 feet because it's all got to be drugged through with a cable. It can't go around bends. Yeah, I just closed because I hadn't switched it for a while. So there's just a lot of different limitations, okay? So this is all electromagnetics. This can combine electromagnetics and ultrasound, but the big difference between the ultrasound on this tool and the ultrasound on these tools, this tool, all the ultrasound technology is based on the centralizer in the middle. One of the issues with ultrasound technology is you have to have, depending on the types of frequencies and the types of sensors you're using, you either have to have the sensors against the pipe wall or you have to have them evenly spaced from the pipe wall using something like water that's got a specific density and specific gravity that you can couple that sensor to the wall. So with this running through your pipe, the data, they have a lot of UT sensors around the centralizer, but the problem is it tends to move like this through the pipe, so it's bouncing around all the time. So the data is very spotty and unreliable in a lot of cases, and there's very little that gets reported at the end of the day. So this tech with the UT sensors, they're placed specifically in the inside of the soft foam pig, which allows them to be equally spaced about 4 inches from the pipe wall, and they always stay at that specific distance from the pipe wall as they're performing the inspection. And they're inside of a soft foam pig that allows them to easily navigate back-to-back 90-degree bends, complex geometry. So that allows you to get these inspections done for a lot less money. This tool is similar in operation to this tool or how it goes through the pipe, except it's zero buoyant, so it stays centered. And then all the UT sensors on this type of inspection tool are out on the wings. So they're actually pushed right up against the pipe wall. So we'll use the Aquabrella tool a lot of times in a 24 to 72 inch like water main, for example. So if we're trying to not stir up stuff on the pipe wall and cause turbidity issues, we'll use something like that versus something like this that's basically we would clean the pipe ahead of time and run a pilot pig through before we launch that through so that we have the pipes clean and we're not pushing a whole lot of debris out during the inspection. So, but we'll go into some of the details about these. So again, the company that that's introducing and partnered with us doing a lot of the new ultrasound technology stuff, which like I said, is going to be part of the next M77 manual, is called the Quaint. This stuff has been out in the market for about 7 years worldwide. They've done over 1,000 miles of inspections and validated everything with a lot of the private utilities, also WETSIS and KWR in the Netherlands, which is similar to like Water Research Foundation and some of the big organizations doing that sort of work here in the United States. So obviously we all kind of, after talking through the first half, we all sort of know what the problems are and the challenges. We've got aging assets. That most recent study from Utah actually said that break rates in certain types of materials like AC, for example, over the past 6 years between the two studies had increased by 45%. I think the average, and it's on the cover of that report if you look it up, if you Google it, the average increase in break rates was like, I think 27% 6 years. So it's been about 4 or 5 years since that published was studied. So it's just getting worse. It's not probably getting better. And I'm sure if you guys are dealing with breaks in your system, you can probably attest to that over the past 10 years. We're looking at theoretical models and real life situations. So we're getting real life absolute data points. Then we're applying that to theoretical and then providing predictive analysis, which is really unique. So, and this is really the key. And you'll sort of see what this looks like when I show you some of this remaining useful life stuff and how it works. But you don't, the trick is you don't want to be fixing pipes that don't need fixed. You just want to fix the pipes that require fixing, and you don't want to have to do it on an emergency basis. So putting all this information together in a way that starts moving you that direction is the idea. So from a preventative standpoint, you've got the like Aquarius tool, the Aquabrella tool that I showed you, the pipe scanner, and then all this stuff goes into what they call their autopilot system to be able to start kind of dialing things in and providing some of the predictive stuff. So kind of back to the beginning a little bit, like if I didn't talk about it that much, like how does ultrasound work? So the sensors, like I said, are going to be placed an equal distance from the pipe wall. You get a reflection off the inner surface and a reflection off the outer surface from the sound wave that's getting put out. And then we're talking about thousands and thousands of readings like per second as the tools are moving through the pipe. It measures that and analyzes it and then spits out a data point. So it could be pipe wall thickness, it could be deflection, it could be ovality, it could be joint gap width. So what that joint gap width. So if you've telescoped a PVC pipe, for example, which is what I explained earlier, where they push it all the way till it stops, that we can see and compare that to your guide standard or specification or the manufacturer's recommended distances or angles. So when they were developing these types of UT tools, what they found was that very low frequencies worked the best, especially when you were looking at materials like that weren't monolithic, like asbestos cement, bar wrap pipe, PCCP pipe. So these are the different sensors that we use for the different material types. You can see there's lots of different types of sensors that work best for specific material types. Okay, so just to kind of share a little bit more information about like this tool, for example, it's called the Aquarius. The system's set up to do anything from about 8 to 54 inch right now. It can be used on any type of pipe. So PVC pipe, FRP pipe, bar wrap, ductile, cast, steel, stuff with linings, with coatings, without. So there's lots of different types of materials that can be used on. And I'll kind of go through what the data points are and what the reporting looks like for some of these. It's a soft foam pig. So if you've ever used like a swab or a cleaning pig to flush out a line, that's basically what the exterior of it looks like. And then all the technology is housed in a centralizer core that's medium density and then also sticking out the back. There's also an internal mapping unit that's got a lot of information that it pulls up that's also on the back, and then odometers. And then these tools all get tracked 100% of the time throughout the entire inspection when you're running them through your pipes. But the risk is relatively low because of the fact that the tools are soft foam and they're not rigid. I've seen situations where you've just got some sort of minor defect in the pipe, like maybe they put too much grout inside of a joint and the grout is sticking out. And if you've got a rigid tool, it might just run right into that grout and get hung up and stuck. So something like this, you don't run those same risks. The other thing that comes up a lot of times, and Dane will probably talk about this in his presentation on valves related to plug valves. If you've got like a rectangular port, like 80% port plug valve, most inspection tools will not go through those. So these tools will go through that type of reduced port valve and also through pipe diameter changes up to 25, 30%, depending on the size of pipe that you're trying to inspect. And then one of the claims, we'll pick up about 95% of the anomalies that would cause problems or distress or failures in your pipes. So this is just a little bit more detail on this specific tool. So you've got the tracking transmitter in the front. It also has a hydrophone. So all the stuff we were talking about with acoustics on the front end, this tool does. All the stuff we were talking about with like the different inspection balls, this tool can do. So it can basically do most of the things we've already talked about with these different survey level tools, but it incorporates it into an inline high resolution inspection. So you get all of this information that I'll go through in more detail. The ultrasonic sensors are on the back. They have to be coupled with water. Like a lot of times we get questions about using these for siphon inspections, which are kind of difficult sometimes, even gravity sewer inspections on bigger diameter. And it's possible. We just have to come up with some creative ways sometimes to keep water flooded behind the tool. So even if we're pulling the tool like with a winch or a cable instead of pushing it with pressure, there's some creative ways we can still get some pretty unusual inspections done. So again, UT, PVCP, polyethylene, PCCP, like 301, 303 pipe, bar wrap, FRP, 854, soft foam. This just shows a typical launch tube. So, and I'll show you some options on how we get these into the pipe, because that's probably a question everybody has. Like, well, those look great. It'd be great if we could send those through different pipes in our system. But like, how do we get them in? How do we get them out? So I'll show you some different options. And this is like a typical launch tube. So you see it's oversized in the top. You would drop the pig into it, pressurize it. That's going to push it down into the main, perform your inspection. And there's usually a guide tray of some kind that we'll have at the other end, the other limit, and then it'll push it up into our inspection port. This is just a brief video, just kind of walks through the process of launching these types of tools that I'll just play real quick. So again, it's pretty simple process. They were tracking it and putting markers out. So you put markers out about every 300 to 500 feet. Oh. But again, anything 8-inch and larger, these things run on, the data collectors run on batteries. So we can go about 12 hours, which gets us about 15 miles at the typical inspection rate of 1 to 2 feet per second, roughly. These can be self-deployed. So if you want to be real aggressive and you want to run these through your system yourselves with a little bit of training, the company and CPM Pipelines, we provide these to clients to self-deploy and inspect as well. And then you can provide that data to your engineering team, your consulting team, like Arcadis, or whoever you're working with. Like I said, we'll pick up about 95% of the different failure mechanisms that can put your pipe in jeopardy. All the different types of materials we can inspect again. So now what's like I said, kind of at the beginning, like what's the deliverable look like? Like, what do you get out of this? So if you do some sort of inspection like this with inline inspections, what do you get? So with a lot of the electromagnetic type inspections, you don't get a lot of raw data. You'll just get the vendor's interpretation of that electromagnetic data. So you're really relying on them to provide you whatever's coming out of their I like to call black box, right? So with ultrasound type inspection tools, you actually get real measurements. So everything that I'm going to go through with some of these deliverables, so all these are so the mapping is the most important first piece. So every single inspection that you would perform with a UT-based inline inspection tool, you'll get very highly sub-meter, like 1.5 foot accurate to center of pipe mapping. So that's really the basis for all the reporting. So once you get that really accurate mapping, we'll compare that to your existing GIS or as-built, so we can see if your existing system's off and we can make those corrections to it to start with. So once we have that, then we start kind of overlaying and laying in all these different data points that we get beyond that. So no matter what type of pipe you're looking at, there's always problems to be had if you have joint issues. Where do most of your failures occur? At or around the joint, right? For obvious reasons. So we can pick up a lot of information when you're looking at different types of electromagnetics. They're blinded at joints in a lot of cases when they're looking at metallic or multi-layer pipes, because there's really heavy armament. Like if you've ever seen a Carnegie joint for a PCCP or a bar wrap pipe, there's heavy armament at the joint. So electromagnetics can't see anything within about 2 feet of either side of every joint. So all they can see is the stuff in the center of the pipe. But a lot of times, if the joint got kicked or offset or there's differential settling, you have all kinds of problems at joints. There was a paper that was written by Dr. Gee, who studied at Virginia Tech, who works for American Water now in Voorhees, New Jersey. He's on the Water Main Condition Assessment Committee with me, and he published this paper, I think, in 2015 or 2016. There was a lot of information about it related to electromagnetics and then also the use of ultrasound, which is why I'd read the paper. But one of the comments he makes is they do a lot of business, or he's done a lot of work with WSSC on the investigative and study type side of things. And they said 85% of all their failures occur at joints. And all they're looking at is in between the joints with the tech they had. So we have a technology, and there's technologies out there now that can get information at the joints that will point to potential problems that your pipe's going to have. So vertical and horizontal angular deflection at the joint, we pick up very precisely within 1/4 of a degree. So if the joints kick this way or kick this way or kick that way at all, we'll be able to pick that up. And then again, these anomalies will get displayed on thermal image HTML maps that are all interactive, that you can basically roll over one of these anomalies and it pops up and tells you everything that's going on at that specific 1/2 meter point throughout that entire pipe alignment. Gap widths. So this can apply to like a PVC pipe if you want to inspect it, so you can see if it's telescoped or not. It can apply to a PCCP or bar wrap pipe where they have to go back and grout the joints. If the grout's missing, like a lot of people don't realize that a lot of the coating, like concrete coating, concrete lining, stuff like that, it's just simply meant to passivate and protect the steel. It's not really there for any other reason. So when that comes out, so if it comes out of the joint, the armament inside the joint's no longer protected and it can start to corrode and deteriorate rapidly. So these things are very important, but most electromagnetic technology, they can't see if grout's missing. They can't see if concrete's missing. All they can see is if there's problems with the steel. So sulfate attack and leaching that's going to occur like on a asbestos cement pipe, these things are all really easy to detect and report on now that weren't available in the past. So leaching, you have leaching occur when you either have issues with the water quality for the product water or the groundwater on the outside, and it just leaches out the materials that create or provide the structural density to the asbestos cement, and then eventually soften or weaken the structure and can fail prematurely. So that's, again, stuff we pick up very precisely, very clearly. So we get scatter graphs, we get bar graphs, lots of different things that show us anytime we're outside of the acceptable range, depending on how we set that up for a specific inspection. This is also something that's really came to light recently when it comes to using ultrasound technology for doing multi-layer pipes. So initially, they thought that you could only see through up to 1 layer at a time, but in fact, if you use the right frequencies and the right type sensors, we can see through multiple layers. So where that becomes really important is, for example, does anybody have like force mains that are ductile, that have like 401 epoxy, for example, or something like that in them? If you do, where the epoxy is already damaged, that's easy to see because we can see the thickness of the steel and we can see the change in dimension to the inside of the pipe real clearly. So basically it would be like seeing ovality in PVC, but we can see that profile. But what you can't see is if it's damaged here, and we can see that through the dimensional readings we take, what about where the like ceramic epoxy liner, for example, is still intact, but maybe because it's corroded away here, it's undercutting it. That you can't see. I mean, I don't care how clean you get the pipe and how not good a camera you have, that even if you cleaned it and you put a camera in, visually you could never see that. But this technology can see that because we can see that delamination that occurs between those 2 layers when you're using a UT sensor and the specific frequencies that are used. So delamination can occur between like an epoxy lining system in steel, or epoxy in ductile, or epoxy in whatever material you want to look at. You see epoxy sometimes coatings or linings on FRP material even, so we can see the separation between those. And most importantly, if you have PCCP or bar wrap inventory, if you start to have an issue with the wire in like an embedded cylinder or a line cylinder, that will likely lead to problems with the can. And eventually you're going to lose, like with a cylinder pipe with pre-stress wire, you're going to lose preload before you have a problem. Once you lose preload, doesn't matter how deteriorated the wires are, until you lose preload, it doesn't matter. And if you lose preload on the system, then those layers start to separate and come apart. Or if you start having a lot of deterioration or corrosion on the can, you start seeing the layers come apart, because that metallic component will actually start to swell. And then that's what causes the two to separate. And we can really clearly see those defects in the pipe and then report them and work those into our useful life calculations. This is just what some of the different delamination layers look like. So this would be steel and concrete core, concrete jacket. This is a representation of like an FRP pipe and shows what when the layers start coming apart, what it looks like. Again, this is kind of a closer look at separation between steel and concrete components. And as you can see up here in the top right, you can't visibly see that. So it's got to be picked up with the UT. So this would be with like an epoxy liner on the inside of an FRP pipe. You can see the separation. So metallic components, we can see the wall thickness real clear. The only time we would have really an issue, like if you had a cement lining and you had a ductile iron pipe or a cement lining with a cast iron pipe, for example, and they were the exact same thickness, like identical, then it's hard sometimes to pick up the reflections on the multiple layers. But otherwise, we get a really clear representation of the remaining thicknesses of both materials. So if you have backfill issues, electromagnetics can't see that. So if the pipe's gone oval, no matter what material type it is, with ultrasound, you can see that ovality in the pipe wall. So especially in PVC pipe, if they didn't backfill it and bed it properly, this will lead to stress in the pipe wall and a failure somewhere between 5 and 30 years out, depending on how bad it is. And what we do whenever we have an anomaly like this, it shows up on the maps that I've been sharing. It's all color coded. And then if we have something serious, we'll break that out and we'll show actually like a 3D thermal image and model of it. Again, I mentioned that this also does have hydrophones, similar to the other acoustic stuff we looked at on board, so we can pick up those leak noises and some other anomalies that you can't with other technologies. We have the internal mapping unit that provides all the really accurate we've got clients back east that are like, can you help us just find the pipes? And we can just run this through, find the pipes, and at the same time, we can get them a full inspection and all the other data along with accurate mapping data. So this was what they were looking at with the paper I mentioned that Lawrence Wynn put out. The inspector in Tucson at Tucson Water was longitudinal bending. And this is what I like to, they say, how do you sell a steak, right? Anybody know? The sizzle, all right? So this is the sizzle. With all this stuff we've been talking about today, all the different tools, all the different technologies, back to the very beginning thing we started with was, what's your goal? What's your mission statement? What's your goal? I know you guys thought I was like all over the place and didn't know where I was going with this, but this kind of brings it all back to what we started with when it comes to this inspection stuff. So at the end of the day, you're trying to figure out what's the remaining useful life. So any other company that's out there, you might get a color-coded map like this that shows you what's green, what's good today, what's orange or fair, and what's red, which you can see a couple of red dots here. So with these remaining useful life calculations, the red usually means you've got something that's in jeopardy of failing somewhere in the next year, roughly. If it's orange, it's usually like 2 to 5, 2 to 10 years. And then if it's out past 10 years, it's green. So what's interesting about what we do, back to the predictive component I talked about early on, this is what that pipe looked like the day it was installed. So it already had problems, right? So it was 1986, and you can't see it probably. And this is 2086. So what this one is I took the slider from day one and slid it out to 100 years based on the inspection that was done around 2020. So now you can go year by year by year and see when those sections start to turn red or in jeopardy of failing within a year. Then you can start making some decisions about where to put that into your budget process and how you're going to come up with the money and what's the liability going to be. Like, when do you need it and how much is it going to be? Because right now you probably have no idea. So until you start pulling a program together, and it doesn't have to be expensive, it doesn't have to be complicated. You can get prioritization type stuff done on the front end free of charge from some of these different companies out there like Suez. Suez is doing some of this stuff. There's basic things you can pull. You can work with your local consultants like Arcadis. They can help with this stuff. So there's lots of resources out there. But the biggest thing is, if you can educate yourselves on some of this stuff, it helps you start trying to figure out what's best for you. Because everybody's different. Every part of the country is different. It doesn't matter where we're at. It's all different. So these are some of the launch tools, retrieval tools for like some of these inline tools. We can actually put a lot of these inspection pigs through a 90-degree hot tap right into the top of the pipe. So we'd have a valve on there. We'd put our launch tube on top of that, put the pig in, close it, hook up the hose, open the valve, press it in with flow, move in the direction we want, and launch it right through with the pipe in service. Deliverables, all the same stuff we've already basically went through. Gap width, angular displacement, ovality, mapping, wall thickness. And then this is just kind of a general dashboard that shows some of the same stuff. So you would toggle these different anomalies on or off as to what you wanted to show up on the map, and it shows up the same as like the remaining useful life calculations. And these are every one of those lines. If you zoom way in close, it's a dot every half a meter is what those lines are reflected in. All right, before I jump into some rehab stuff for like the next 20 minutes, anybody got any questions that you'd like me to answer about inspections or pressure pipe or tools or anything? I usually at least have one person that's planned to cause me problems, but not here. Okay. Well, hopefully that means I covered it all. I doubt that, but all right. So it depends on size. So you're going to have kind of a mobilization and a base cost associated with any of the different tools, whether it's ours or somebody else's. Then like the per foot charge on like our inspections, for example, that provide everything we've talked about this last 30, 40 minutes is like $3 a foot. So, all in. So the key is, if don't do 5,000 feet if there's 20,000 feet that can be done, because the 5,000 feet might cost you $150,000. And then to do 20,000 feet, it's only going to cost you $200,000. So your cost per foot goes down dramatically. So that's the one thing to always keep in mind, is the reporting side of it's inexpensive. It's that upfront stuff just loaded into the cost of these projects. And then also there's creative ways to incorporate the inspections with, like, for example, maybe you've got a bunch of butterfly valves in line, they're all in bad condition. So you don't do the inspection because you want to use something that's high resolution like this, but can't pass a butterfly valve. So you could go ahead and plan, if the pipe's bad, your valves are probably bad. So get the valves changed, spend some capital money, make the changes you need now that'll allow you to continue to do these every 5 or 10 years down the road, and kind of push that off into your capital budget sometimes, just making the necessary modifications so you can kind of keep that separate from your inspection costs. So just something to think about. So on the trenchless side, again, the gravity stuff, there's a lot of stuff that's been out there for years, right? Lots of cured in place pipe solutions, there's some fold and form plastic pipe stuff, there's fusible PVC, there's HDPE, just loose fit, where you just basically hook up a piece of polyethylene pipe, pull it into your existing pipe and terminate it somehow. Can't go through a lot of this stuff, you can't go through bins or offsets or anything like that though. So in the last 25 years worldwide, they've introduced a system called FFRP. So this just got coined recently with the introduction of a draft at ASTM that's being developed right now for FFRP, which are flexible fabric reinforced pipes. And there's also a draft being developed with AWWA and the pipeline rehab committee that's chaired by Dr. Mo Najafi, who runs the engineering and materials testing program at UT Arlington. Okay, so these things have come a long way. We've been doing this type of work for about 10 years. We've done over 125 projects, but it's becoming a lot more mainstream. So the bullet liner system is the FFRP system that we use. There's also some specialty CIPP stuff. There's point repairs you can do. Actually, Avondale, we're gonna be out there, I don't know, a few weeks doing a point repair where I think you guys had a boring contractor drill a hole through your pipe, and we're going to put an internal seal over it to patch it up. So there's a lot of different things out there, and we kind of try to stay on top of a lot of the new stuff. So this is just happens to be the one we offer. There's another one out there that's available, but this is what we have for a lot of different reasons. We use this one, but you can put up to 1,300, and this is what this is if you guys want to pass that around while I'm talking about it, just to get you an idea. So we can put up to 1,300 feet in an hour. We can pull up to 8 to 10,000 feet in one continuous pull. One thing we talked about earlier was construction related damage, right? And that 95% of probably all the failures we've seen and things we see when we do inspection are all construction related. And it's not intentional. It's not like people are going out and intentionally doing this stuff. It just happens. The reason these type products have never had a failure that I'm aware of in 25 years of installations around the world is because you can pull 2,000, 3,000, 4,000, 5,000 feet at one time, and you have two joints. One on this end and one on that end. So if you think about that, if you put 5,000 feet of ductile pipe in at 20-foot sticks, how many joints do you have that could potentially leak? They all got put together by people. A lot, right? So that's why this has been so successful. The joint, the way you terminate it at the termination points and the way you put the joints together is super simple. It's really easy. I've basically built the construction side of my business around this simple system. So it works really well. There used to be just the one option for like water, wastewater. This is an option that's out there now for high temperature stuff. So you can put this in anything up to 230 degrees Fahrenheit. Who runs water plants? Some of you guys got water plants? A couple guys. You got aeration systems, right? Blowers? Like here in the Valley, huge problem. We've done all kinds of repair jobs on blower lines at water plants because they put gasketed joints. They didn't put high temperature gaskets in it because nobody was paying attention, or the contractor just put standard stuff in. The gasketed joints dried out, went bad. Then guess what happens? Then you can't turn the blower off, because if you do, you start getting condensation in your steel pipe, and then your steel pipe starts to accelerate the corrosion really fast. So then they just have to keep the blowers running. So what we used to do was go in and open up a couple of spots several thousand feet away, and we put internal couplings with high temperature gaskets at every single joint. Now we can pull that into the entire run, put a fitting on one end, a fitting on the other end, put it back in service, and your blower's working efficiently again. This just shows the difference between the two different types of options that you guys have out there. These are all, both these options are going to be part of these new standards that we're involved in writing. So the one on the left is not the system you have in your hand. This is the one you have in your hand. This is the one we've worked with in the past. The biggest difference, if you look at that blue sample as it passes by, the jacket and the liner are embedded in the fabric weave. So that's why it's flexible fabric reinforced pipe. The inner core is either polyester or Kevlar or a combination of the two woven fabric. And then they embed the modified polyethylene jacket and liner into the weave. So what that does is it acts like reinforcement in concrete, basically. So this one, you have 3 very separate layers. And I've got a piece in my bag that's ripped apart, but I'll leave it. But these different layers, so you have a black inner layer, a fabric layer, and a jacket, but they're all made separate and they're put together with adhesive. We use that system successfully for 8 years, works great. We switched to this one in the last couple years because this only goes to 20-inch, the old system, because what happens is as you start putting more weight to the liner, it'll actually start pulling itself apart. So with the bullet liner system we use now, we can go all the way up to 48-inch rehab, up to 2,000 foot shots at 48-inch, going through multiple vertical realignments and offsets and bends. So this is just some of the technical information for these type liners. Just shows the material types, the standard pressure ratings, but all this stuff is project and design specific. So for installing this sort of stuff, you basically just have 2 pits, one on either end, 10 by 10 by 10 roughly. You cut out about 7 to 8 feet of pipe, you camera it, clean it, pull the liner through, terminate it. So very minimal impact to businesses, the environment, homes and residential areas. So your footprint is very small and you can complete these projects. Just to give you a couple of examples, we put some budget numbers together for about 12,000 feet of 16-inch on a force main here close to the valley recently. The replacement cost on that main was going to be about $8 million and probably take 6 months, I bet, and have to rip up 2 miles of a major thoroughfare. You could use this type of system for about $2.5 million, probably get it done in about 6 weeks and only have 6 pits throughout the whole alignment of 2 miles. So it's just much quicker, much less impact. Yeah. Yeah, it's NSF 61 approved. So it can be used for drinking water, can be used for raw water, can be used for reuse water, can be used for sewer force mains, gas, oil, hydrocarbons. We've got several other different options I can show you. This is the kind of geometry we can pull these pipes through. So I think a picture says it all. And then the fitting systems are really simple. You basically have a 2-piece fitting system that presses together with a hydraulic press. So they're really simple to put together. These are all 3 systems for the 2 different companies that make them. This is a compression system for the system we used to use. This is a high pressure system for the system we used to use. And then this is the bullet liner system we use currently. And this is either just a two fitting, or it's a fitting, a ferrule that goes on the inside of your liner once you cut it, and then a press piece that goes behind it. So they just press together with a hydraulic press. And this just demonstrates the different in diameters of the different systems. So the one on the left, this is a job we did in the past. So you've got, it's 16 nominal, but that's 17.4 ductile OD. This liner's 13.68 ID, and their fitting attaches to it as 12. The bullet liner system that's available now, the ID of the pipe is 15.12 and the ID of the fittings are 15.12. So the two match, so they're the same. But you can see this, you could use one size smaller and still have a bigger diameter than the other system. So that's one of the reasons we started using this one. So 2 to 48 inches, 5-year warranty. There's no other system piping wise that gives you more than a year warranty. 50-year design life, which is about typical anymore for what you're seeing. If you look at studies that are being done. Is that back on? There we go. I just talked too long. But 50-year warranty or 50-year design, 5-year warranty, which is typical, like the studies I've been referencing, like Utah State, they say most of the materials anymore going in the ground, especially like on wastewater, sewer force mains, you're probably lucky to get 50 years out of them. And there's been gas technical institute studies that show these liners last them well over 100 years in applications. So again, no reported failures on these type systems in 25 years. And I really attribute that to the fact that with my experience on pipe inspection and rehab, the fact that there's only a couple of joints for every 1,000, 2,000, 3,000 foot section you put in the ground. These are the 4 different systems, Jason. So you've got the blue that's for the stuff we just mentioned. Then you've got yellow for gas mains, O for like hydrocarbons, oil, gasoline, and then H is the high temperature system. Yeah. Yeah, so he asked what kind of cleaning has to be done. We just can't have anything sharp inside the pipe. So we don't have to have it blast cleaned or blast finished cleaned to like a white finish or anything like that. We just can't have anything sharp. So we use like drag scrapers, spring loaded scrapers. We use pigs. A lot of times we do a lot of rehab on PVC pipes because the last 10 years they'll start popping and they can't have it pop in a critical corridor. So we'll just go put 1,000 feet of that in. And when we're doing PVC pipe, we hardly have to do anything. Like I can't remember ever even having to run a swab pig through them because there's nothing in them. You know, it's not like a steel pipe that's got heavy tuberculation. Now that takes some work, but that's what we've figured out over the last, 10 years. Like, it's already what? Right, yeah. Yep. Yeah, as long as it's still there. And then as soon as we take the pressure off of it, if it were to crack later, it's fine. Because if you think about it, like I've had this like debate and discussion with a lot of these PhD professors that work at a lot of these design institutes, like Tom Isley, Dr. Isley, who's at Purdue, Dr. Najafi at UT Arlington, Dr. John Matthews, who's with the International Society of Trenchless Tech, and he also runs the Louisiana Tech Trenchless Technology Center. But if you think about it, you don't see pipes fail from collapses. Pipes typically don't collapse. Pipes fail from pressure, right? Pressure is what kills pipes at the end of the day. It's not earth load. So generally, if you take the pressure off, yeah, if you've got a lot of taps or tees, like if you had a subdivision, yeah, if you had a neighborhood that you had a tap every 100 feet, this probably isn't the perfect solution. Could be, but probably not. But if you have a tee, you just have to terminate it at those tees and drop a tee in. So it's easy. And these fittings, just to give you guys an idea how quick this stuff goes in, Monday in Maricopa with Global Water, we had the pipe ready to go, pits opened up, showed up at 6:30 in the morning on Monday with my crew. We had 200 feet of liner pulled through 445s, installed, aired up because we fold it up and then you put air on it, it just blows it back perfectly round. So we had it pulled in, aired up, and both fittings put on and done by 2:30 in the afternoon. 200 feet of brand new 24-inch pipe through ductile pipe that was going under a ditch that they couldn't get to test. Yeah. Yeah, cut it. Yep. Yep. Oh, no. So that specific pipe had never been put in service. It got put in and then let set, and then they can't rip it out because of being under the ditch, the irrigation ditch. So they had to figure out a way to fix it. And the only way to fix it was to pull a new pipe through the whole 200-foot section. But yeah, if it is badly degraded, we'll go back in and we'll clean it and fix it if need be. But most of the time, there's a lot of good information coming out about these, and we can even combine, like you can actually take, for example, a 48-inch standard liner that maybe is only rated to 100 working pressure, but has like a 2 or 3 to 1 safety factor built into that. But you can put that in a 500 PSI 48-inch pipe, for example, and that'll blow right up against the pipe wall and then actually act as just a liner that kind of separates the media from the hose pipe. And we've done that and had those installed for 7, 8, 9 years now, operating like a 100 PSI or 250 PSI liner and a 750 PSI pipe, operating fine, because once you take the pressure off the actual pipe, you don't have to worry about pinholes blowing out where you've got localized pitting or corrosion. So it just, if you think it through, it solves a lot of the problems that and how those pipes tend to fail. All right, I think I was almost like I planned it for 2 hours. But so that's me, Chris McDonald, CPM Pipelines. That's my phone number. That's my email. These guys know how to get a hold of me. So I can't tell you, like Jason said, he knows I'm gone a lot and I'm on the road a lot, but I'm from here. I live here. My company's here. And I appreciate you guys giving us a chance to come out and talk, share some of the latest and greatest technology that big cities all over the country haven't even seen a lot of this stuff. And just remember, there's cost-effective ways to do this. There's a lot of information out there that you can pull up for free. And if you're interested in any of the studies or publications or reports I've mentioned, I'm happy to share them with you. Just take my email, send me a message, and I'll send it to you. Questions? I only left you a minute, but I didn't think anybody was asking questions, so. You don't. It's just like you saw. It gets made like that. It gets manufactured like that. That one's oval because it was flattened and rolled up and wasn't inflated. So if I take that and I put air pressure on it, it'll blow it perfectly round. And it's stiff. You saw how stiff it is. So you have to cure, fiberglass or whatever backed impregnated with resin pipe because the resin has to harden. So this doesn't have resin in it. It's just woven fabric. Yep. Anybody else? No? All right. Well, thank you. I appreciate it.
All right, thank you, everyone. Thank you, Chris. That was an amazing presentation. So at this time, it's only on 11 a.m. and we're going to start our hour break. This is lunchtime. If you need to go somewhere, grab a snack, take a walk. There are a few places locally, but there's a really good sandwich shop south and to the right of ADEQ. What's it called? On the other side of Jefferson, right? Yes. So going down Washington. It is within walking distance. Ironically, you might have to pass a graveyard, I think. But don't let that deter you. Those sandwiches are amazing. But yeah, we'll be back here at noon and we'll start with our next presentation with Arcadis.
We are recording. Show the screen. Perfect.
We have all right. All right, let's rock and roll then. All right, let's see. All right. Welcome back, everyone. Just a real quick introduction. My name is Dave Whitmer, engineer for Arcadis. I apologize for our colors. It's supposed to be bright and I'm just bright and noisy, so I've been with Arcadis here for about 4 years. I've grown here myself and different things. Pretty broad. I would never say I'm an expert in one thing, but I have, I've been doing work inside the fence, outside the fence, and yeah, so hopefully I can provide some insights to what I've learned over the years, and we're going to go through some basics. Today's topic, distribution valve. If you've ever gone through PWA M44, that's a lot of kind of where this presentation will go through. So introduction back to valves, and while we is that better? All right. So we'll go through that and some other things that I've seen as I've been out in the field and looked at assessments and stuff like that. Again, designing pipe systems, inspection of them, consistent both on water, wastewater side. Anyways, myself, all trade master now, so I'm happy to learn something new and get it done. Anyways, so next, some of the topics, like I said, we'll go over a WWA M44, go over some of the types of valves that are going to see out in your distribution system, some of the material selection considerations that we'll do for those, installation testing, and then we'll also touch on a couple of the specialty valves which I think are some of your important valves that you can consider and keep up on. All right, so what do you think that is? No worries. All right. Anybody give me an answer? What do you think that is? Let's see. All the way in the back here. I'll give you points for trying at Stafford. don't add this. There's no T in there. But no, this is actually a valve used in Pompeii about 100 BC. So this, it's made out of bronze, right? The Bronze Age led to a lot of this stuff. And they ran their system probably about 4 to 6 psi. It was used to, you were considered luxury. You could have water delivered to your house. And they used these to throttle the system and actually control the flows and make sure that they had proper water pressure to their home, bathhouses, fountains. So yeah, valve been around for quite some time. I am not being sarcastic. No, this is 100. This was about 100. About 100 BC. There's evidence out there of valves being used. I just did a Google search and found this one. But let's see. Here's kind of a timeline of valves that comes out of that AWWA M44 manual. So about 600 BC, showing that there's been flat type valves, plug type valve that shows something similar, goes all the way back to 400 BC. The valves were used, probably like some kind of diaphragm pump conditioned with a set of check valves that helps with pumping. Was developed about 50, and then about 100 BC, Alexander develops the first workable valve. What comes into or no, we'll start seeing actually the technology of the first wedge type valve, 1839. That figure there on the left is by James Nasmith that developed the London Waterworks. Hey, I need a new valve. I need something better. And this inventor went to work and came up with, greatly appreciated that it essentially became the standard for several years. Took a little while, essentially, before there was kind of an improvement. 1805 is where you brought in this valve. AWWA, the standard for steel or metal steel valves, AWWA 500, about 1980. Those kind of guys around there. Another plug that I'd like to for operators and people in this industry, exactly how important is the history of what we're doing. This idea of disinfection. George Fuller trained. You learned about this there, brought it over into the United States, Jersey Waterworks, or the city of Jersey City, and which prior to their water, George introduced hydrochloride sections. Worked so well that it started to implement. So over the next 20, 30 years, turn of the 19th century, or 1900, nearly all water were from water source. So when I think about what has really changed in life, I think of disinfection as probably the biggest thing ever. And that you all take a role in protection of human health and environment. So I appreciate a lot of those that take effort in making sure that our community is on board just on the idea of water and water. A little bit down the road, finally get a more modern valve. I brought a 4-inch valve from Corner Main they borrowed. I was planning on taking it apart, but time, and I'm not going to But anyways, so we got see the gate valve about the 90s. That's been kind of a mainstream. Typical type of valves. They're broken into two different ways, or two different types. We have flow control valves, one that you'll throttle for either flow or pressure. Then you have your a more traditional isolation or direct shut-off valves, just an on-off kind of designation. There's the feed out to the foot of the control valve and what it shut-off valve. But off the top of the list, valves, piston valves, butterfly, diaphragm, pinch and ball valves can all, with appropriate use, be used as a control valve. Of course, they can also be used as shut-off valve. But more specifically, we can start looking at shut-off valve. Your gate valves, or quarter turn plug and cone valves can also are going to be the more type valve and providing your zero type approach. So let's see first valve here. The flow valve. Things about the flow valve. It's been around for a while. It's called a glow valve because the body used to have a bulbous shape to it, so it kind of got that name. That's not the case anymore. It can have different forms. It can be a little more streamlined. It's very the regulation. It has a high sealing capacity, pretty resistant to wear, although it can be, if there's fibrous materials or other things in there, debris can also, or even, everyone has a faucet at home, right? You leave it open for a while, it gets calcium buildup on that piece, it doesn't seal right. So that's something that valves are prone to doing. And so it doesn't handle the small debris well. It's very kind of precise. We'll talk about it a little bit more. But everyone's seen the pressure regulating valve using our flow control valve, right? So the inside of it is nothing more than a flow valve with an operator associated with it. And we'll talk a little bit more about that. That's the same shape that we can kind of see in there. Technical difficulties here. I need to stand over here, but my notes are right there. So try and be careful with this. So I would like to get as much as I can, because one thing about being in this industry is sharing of. And so like what people have experienced with these type of valves, something that you feel is beneficial to one another. So like the valve, where do you see them mostly? Just see them kind of in that shape as a control valve, or do you see it as a manual somewhere on pumps or tanks, or what's been your experience with them? Jim? Plug or okay? Did I say? I meant globe. I meant globe. I'm talking about globe. It's a problem with my brain, but it's thinking 10 steps ahead of my mouth. It overrides what my mouth is going to say. Bells. Good experience, bad experience. Hard to maintain. Easy. Okay. The pump control valve controls come pretty regularly. Yeah, that is one thing about these valves. I'll talk a little bit more about those things, but you're correct. They are a fitting valve and do require quite a bit of maintenance when they're used in a pilot automation. All right, so this valve the butterfly valve. Very simple in design, has a different couple of shapes. You can get more information about it by picking up AWWA C504. That's also the standard in which the valve should be. I've typically used it as an on-off type valve. It does have some throttling capability. I've used it typically in a condition when making a valve is too expensive. And so I'll switch over to, you can see that there's a lot less advanced to the valve, that it requires less metal, machining. And so it ends up being a cheaper valve, but it still functions very well as your shutoff. There are some things to consider when looking at it from the engineer or the supply side, what pressure you have to get. It's not just a one size fits all thing. There are some options to consider, whether it's an offset type valve, double or triple offsets. You can see the materials in there. The can be metal, and then it's coated in rubber, as well as having you have your operator. The other thing is that it'll have this is a flange type of connection. This will probably be mostly buried tight. I don't know if I've ever spec'd out a butterfly valve. Anybody done that before? I don't know if I've above ground, very essentially it's just a pipe, and so again, another way to save costs. Yeah, most valves right. So if you have a smart, it's going to give you a dismount right there by the wafer valve. That way you can slide it back. Again, not all engineers are up here. It's important for you all to be very proactive with your design teams, take the effort to look in there. What will work, what's not going to work, sit down with them. Engineers just want to be like you. That's what I tell all my juniors. It's like, you want to be an operator, think like them, be like them the best you can, get out there, look at what's going on, talk with you all. So be proactive. You do have a lot of value. You are professionals in this field. So please, I appreciate that comment a lot. Or, puts out a very good point. Disadvantages, it is in the flow pathway of these valves, so it does create a blockage. Chris was talking about some of the things that he does. This valve stops some of those protection tools. It's better if you turn that valve on the side. It helps with rolling that ball through the system. You have less chance of it jamming between the bottom pivot. It does have some size to it, so you have to make sure you consider, and from a design point of view, that if you turn that valve on the side, that you have enough room in your trench to put in that operator, and then also be aware that that you're not sure where your pipe is in relation to your valve can. So if you go digging, your pipe is going to be where your valve can is. There's going to be an offset to it, and you can be digging in the wrong spot, and problems can happen there. All right. A question I came up with. A lot of times, so we use flange connections on butterfly valves. Do we like to bury? A question: do we like to bury flanges? What's your opinion? Yes or no? Give me a thumbs up for yes, thumbs down for no. All right, 2 votes, just like our election. So we got a no in there. Sorry, I can't help myself sometimes. If I offend you, just tell me. I'm sorry. So no. Why don't you want to bury a flange? Erosion is one of them. accessibility, or did I hear flexibility? Okay, both. Yeah. Right. Yeah. So it is a lot of bolting material in there. My biggest point of view is it's a rigid fixed connection. So if there is any kind of poor installation, it ends up distributing forces across the pipe a little bit more. So I like for a joint to be able to move a little bit. So that's why we like to use a slip or an MJ type connection in a buried condition. Up above doesn't matter. We have visualization on it. We know where we can support it and take care of it a little bit more. All right, next one. Ball valves. Are relatively new in the idea as a control. There's been some advancements to it. And, let's see, this one is Valvematic. Reading their literature, they really try to sell the automation of it or the control side of it. But that automation requires a lot of electronic sensing and solenoid valves. So it's essentially doing what this valve does, just with pressure sensors and solenoids. So you look at this as a control valve, it has to be said that it can be used as a control valve. So work with your suppliers, make sure that they say, yeah, it is. Otherwise, like your PVC ball valve that you're going to get off from Home Depot, wherever, it's not going to be the best throttling valve. We like ball valves. If I could use them, if they were more common, I would. And that's just because it's a full port opening. They're real smooth, very little head losses with it. I've been kind of putting in there that key value of for the gate valve, that was anywhere from like 6 to 10. That represents kind of how much turbulence is in that created by that valve, right? The ball valve all the way down to 1, so 1/10 of or less of the turbulence that will be created through that opening. So it can be an energy saver in that kind of idea, but they do get very expensive as you go up in size. So you wouldn't see as much past 8 to 10 inches in use in any kind of field, unless you have a very specific need, have high velocities, they'll go with that, dam spillways, the way that they, or outlets that they goes on. But when you're building a dam, you have a damn lot of money. Yes. So again, it's a full port opening, so you can clean right through it. Let's see. With these ball valves and quarter turn type valves, you do run a risk of actually creating water hammer if you close them too fast. Whereas if you're working with something with a gearbox, you just have to make sure you specify, a slower closing rate. Is that gonna work better? I think I hear it over here. Let's see. All right, so diaphragm valves, pinch valves, not really used in the water industry. You're probably going to see them high solid line, but they're very simple. You can see the one on the left that is completely open. All it's doing is it's just pinching a rubber tube and closing it off. So, like I said, real simple. Because it's made completely out of rubber and you have no operating parts in a wetted area, it's very corrosion resistant. The problem with that is if you do try to use it for control, you actually have to start deforming the shape fairly far, past 50% before you actually start seeing things, because then you're just ovaling the pipe. You're keeping the same surface area or the same opening area until you start actually pitching it smaller. They can be expensive. Small pipe applications, they do have some velocity limitations. The diaphragm valve is it actually has a seating surface that protrudes into the valve itself, and the diaphragm closes on top of it to cause that closure and that restriction. You do have these type of pitch valves. Those are air operated, and they're pretty good at handling, like I said, solids that press the tire or tube across the material that might control it. It definitely does have a higher head loss on the diaphragm, of course, with the other ones, the tubes, those are full size diameter, so it doesn't have any impedance. All right. All right, getting back into gate valves. Like I said, there's 3 standards out there for the gate valve. AWA C500, which is your metal seated gate valves. AWA, again, so that was based off of the wedge valve that was invented back near the end of the 1800s, right? Also covered double discs. And then resilience developed, and we had AWA C509 that was developed about 1950s to the and on up. Then later we started saying, look, everything was based off of cast iron materials. We have ductile iron now. It's stronger. We can thin it out and still maintain the pressures. So they developed a newer version of AWA C550. So there's a lot of history. Kind of the idea is it takes quite a while to catch up with ourselves, because ductile iron's been around since the 60s, 70s, right? It's kind of the same idea as road trips. We know how wide road trips are. Where did that come from? And stuff, right? So it came because they were doing railroads. All the shops were set up to be cartwheels, right? And they said, well, where did that come from? It actually comes back from one of the Caesars who said the cylinder was Roman trim, 4 feet, 8.5 inches wide. And so forever, that's how we now have the same width as a railroad track. So sometimes catch up, things will get a shift in it. And I take gate valves as kind of that idea, right? Since 1800s, we had metal seated valves. We want to try and switch this. All right, let's try that. Have just such a great I don't think so. Is it recording off of this? Can be. All right. We'll just. Do I need okay. Told you that was annoying. All All right, so the C900 or C500 design standard was developed based on the physical characteristics of cast iron. AWA C515 was based on the more robust physical characteristics of iron. And yeah, C509 was developed in 1980, and then yeah, it was 1980. 500 was adopted. Anyways, so what makes it a resilient seated pay valve? Anybody have an idea? Or what makes it a double disc valve, or what makes it a wedge valve, or what makes it metal seated valve? All right. So it really gets down to, you have to really kind of look at the valve, inside the valve itself, and how it's operated. So a wedge type valve, you would see a metal wedge inside of there, and it's going to actually be a recess at the very bottom that valve will sit into. And that wedge, as it pushes down in, is going to force itself against the metal seat, and that's going to create the sealing surface. With double disc, what they've done is that they've put kind of a cam between two discs, and in the wedge type fashion, as they push it down, the water will actually fill in behind whatever the upstream or the downstream valve or the downstream seat, and it'll push it against the that downstream face. And so typically the higher the pressure, the better the seating is on those double disc. Conversely though, double disc and wedge valves are notoriously hard to operate, to break open and get moving. So if you do have them in your system, you need to operate them more regularly. You know, typically you can get away with like a resilient valve operating at once a year. Double discs or in metal seated face or metal seated valves, you'll probably want to do at least twice a year. You don't really see them out there much, the C500s. Some people, again, still do the chariot wheel, right? It's been there forever. It works for them. I know only a couple of companies out there that will provide them to you. So Mueller is one of them. This is their double disc valve. You can kind of see what I'm talking about. It does have this wider body for the bigger disc to go in, and then you can slightly see the curve there at the bottom where that recession where the seating face needs to go into. You can see it in the valve that I brought with me, but the resilient seat doesn't have a recess into it. You'll typically see the disc coated in a rubber material. Conversely, I think some of the older style, the seating face is actually on the body of the valve rather than you'll still see a metal disc. But I think the key is that you're going to be using a rubber sealing surface to shut off your water. And you know, there's pros and cons in there. Positive with it is that it is a full open flow through type valve. It does get expensive after you start getting in the 20-24 inch range, and so then you'll start moving into the butterflies. It does offer good corrosion resistant, again, because everything gets encapsulated, everything's coated. It does offer bi-directional seating, so it doesn't matter if it's forward or backwards. Disadvantage with the metal seats, again, like I said, needs more time to open. Not really designed for throttling, and does have some high velocity limitations. Yes.
What's the notch for? The notch on the valve?
These notches. What are the notches on the valves? So this is something I don't know. I'm trying to see if it's an MJ type connection. I think it's an MJ type connection. And so you don't have a, yeah. So with this, you're not, with, the question was, in the photo here, what is the notch in the metal seated valve, the blue valve on the right? Yep. Yeah, so this isn't going to be a full face gasket. This is going to be a mechanical seal. So it uses a lug to push in an O-ring against the body of the valve. Go ahead. I like it to be in the vertical position. You can put it in other places. Say it again. You can put it, I've seen them done horizontal. The thing that I don't like about it is that if it's got sediment in the line, it's going to settle inside the bonnet. It's going to be in the bonnet. So that's why I like it to be in the preferred in the vertical position. But I have seen them definitely not buried. I haven't seen them. I don't want to put them on its side, but you know, up above ground or something, you can put them to the side if you need to fit it. Again, that's just what you'll need to do though, is keep that in mind. Any other questions? All right, let's see what we got next here. All right, some of the ideas between the metal seat versus the really resilient seat on the next slide. Again, if you're running very high temperatures, and we're talking steam temperatures, boiler temperatures, you know, a metal seat is still a valid thing to do. Rubbers have a actual working temperature. But again, you know, you imagine a machined face against another machined face. If there's little breeze in there, it might not allow it to close. Also, that divot in the disc valves or metal seated valves, that actually is a place for debris to also catch. And so over time, if you're carrying a silt load or some extra turbidity that settles in there, it might prevent that wedge from going all the way down in and creating a solid seat. The great thing about the gate valves, resilient seats, they are very consistent in providing zero leak, but they can be attacked with certain chemicals. We use a lot of them in our systems, right? But making sure we specify the right materials to be chemical resistant is important. So for example, I'll talk about it a little bit here in a bit, but Buna N versus EPDM. Buna N is a great material, works really good in 99% of the applications. I like EPDM though on my water distribution systems because it's just it sketches out or ekes out a little bit better in resisting chlorine. Buna N does much better in a wastewater application because it's more resistant to fats, oils, and greases. So just a little plug on that. Let's see. Lost my spot. All right, next one, plug valves. So who uses plug valves? What do you use plug valves on? Yeah. So this, you're not going to see this in the potable side. You'll definitely see this in the wastewater side everywhere. And the reason is that these handle solids very, very well. You might be able to barely see it right here, but that's the seating face. It's like a big window or door. And when it closes, it closes in around the orifice. You can get these valves either full port or eccentric. And so that just refers to that the opening space, if it's eccentric plug valve, the opening is probably about 70 to 80% full opening. And it's not round opening, right? It's more like a trapezoid. If it's full port, it's going to be rectangular. So again, even though it's a full port or full opening in the same area as your pipe, it's going to have some restrictions in your pigging operations if that's what you're doing. So handles heavy debris very well, some throttling, but not really. Again, wastewater, it's going to be a very large and heavy valve. You can get these all in stainless if you really wanted to spend 10 times more money, 20 times more money, whatever it is. I think I was looking at putting some in some aeration basin as a drain valve, and I think they went from like $3,000 to the valve for a 12-inch up, and then for just a regular valve, and then it was $12,000 for 316 stainless. But sometimes you need them, like if you're on digester gas or other things that are highly corrosive. So that option's out there. All right. Valve configuration installations, just some tips and tricks here. Next slide. End connections. What are the 3 most common type of end connections? I gave you a hint right there. Brownie points. Man, I should have brought my kids candy. Dude, my kids brought home like 30 pounds of candy with 4 of them. I was just like, and they don't care if I throw it away because I got more. All right, so end type connections. Most common ones, bell, push on, or slip by socket, mechanical joint, and flange type connections. What's your favorite type of connection in a buried application? Slip, easy, right? You can put it together. What's the problem with that though? What do we run into with slip connections? It's the what? Yep. Yeah, there's definitely that. It's leaks. It also from the engineering side, it's not restrained, right? You have to have additional hardware to make it restrained. But if everything's all good, then you can use them pretty fairly well. So most common type in your buried is going to be a mechanical joint. It has about the same amount of flexibility in it. You look at a manufacturer's literature, they'll probably say that you can deflect a mechanical or a slip joint about 4 degrees. I don't ever recommend letting that happen with your contractors or in your specs. At the most, I'd only let it be half, because I've seen them, contractors come in and mostly in the developments, right? Or other people that you're not watching over, and they'll use their excavator to bend the pipe around a radius, and so you have to really be on them and make sure that they're not overdoing what you give them. So if you give them the full, right, they're going to go probably past that. So then also tell your engineers, look, make sure that you're not creating a radius and just drawing a radius on a drawing and assuming the contractor is going to know where to put a fitting. So again, be involved everywhere that we can. Restrained versus unrestrained. How many use mega lugs or the type? How many don't know what a mega lug is? I can appreciate that. So I didn't bring a picture, but there's restrained and unrestrained joints. A restrained joint means that we're actually locking the pieces of pipe together, and we're using some kind of mechanical mechanism to hold that fitting or the pipe together. In a mechanical situation, what we end up doing, I don't have what the fitting is, but we essentially have a gland that fits on this side of the pipe and an O-ring, and that gland cinches to the face of this valve and wedges that O-ring into the fitting or the valve. When we want to make it restrained, there's there's different manufacturers out there. Common is a mega lug, but they actually screw a wedge into the pipe like a serrated tooth, and there's a number of them all around the pipe, and it actually grips the pipe and holds it into place. And so that's what it is. you have to be very specific. Not all types of pipe, right? Plastic, ductile iron, steel, you can use them, but you have to specify what material they are, right? So there is a certain consideration you need to give for what that is. There's other types of restraints out there. You can do collars. You can do tie rods. I don't recommend tie rods in a buried situation. The gripper type restraint like a mega lug is probably going to be the most preferred. It does add time, it adds material, it adds cost to put those in. We do have standards out there to follow. Maricopa Association of Governments. I think I haven't looked at Pima counties. Does Pima have a restraint table in their standard? So it's a great place to start if you're having to do inspections, look at drawings, look at these standards, make sure they're being followed. Let's see. The idea, so then a little bit about flanges. You've probably heard of AWWA flanges and ANSI flanges. ANSI flanges are developed actually for the oil, gas, and steam industry, right? So they are developed under the notion that these flanges are going to be under pressure and at much higher temperatures. So 150-pound ANSI flange, you might hear that term, does not mean that it's 150 pounds working pressure. It's probably closer to like 400 at normal atmospheric temperatures, right? An AWWA flange does not account for temperature and material weaknesses. And so it's rated for typical normal water pipe operations. So in general, when you see an ANSI flange, it's typically going to meet an AWWA preference. Drilling hole patterns are the same. It just ends up being different thicknesses. On the converse side, ANSI flanges only go up to, I think, 24 inches diameter. And so anything past that we use, AWWA goes up to like 72 inches. And then they have different pressure classes that they designate by a letter, B, C, D, E, and on up to F. D's probably, I think D's the most common. And that's going to be, I think that's going to be 100 and, I wonder if I wrote it down here. No, I didn't. Yeah, 150, but for ANSI, 150-pound flange is rated at 200 degrees Fahrenheit for 260 PSI. All right, just to kind of give you the difference of what's going on with them. So restrained joints, the only one that's always restrained is going to be the flange joint, unless you add in an additional restraining system on one or the other type flanges or joints. Materials, we want to make sure that we're lead-free, NSF 61, or has AWWA markers to them. For the rubber materials, we talked a little bit about that, unit N versus EPDM. Ductile versus cast iron. When was ductile iron kind of being introduced? 1970s, right? So it's come, and before that was cast iron. So you see a lot, go ahead. Are you talking about the torque? You're talking about the torque. That's beyond my wheelhouse. So you'd have to talk with a rep about that. So I'm just, like I said, I'm just the idiot engineer. So there is, right. So I chair the water distribution committee, and so I've worked a little bit alongside one of their water supervisors for the town of Gilbert, Steve Notch. Don't know if anyone knows him. Do you have another question? So yeah. Yeah, there's yeah. So that would, if it's getting, you know, you'll talk with your manufacturer and you'll kind of get a range. You'll start realizing that once you get past something, that you'll just say that that valve's dead, right? It's got to be replaced. What I was going to say, that the town of Gilbert has a pretty good asset management program, and they actually have a valve truck, and it's pretty slick. That you know, they'll stick that. They actually have an operator that when they go out there, they find the valve. It connects with their computer maintenance system. And so it'll log the location, it'll log the time that they're there, it'll log the torque that was put on that valve, and it'll log the number of turns it takes. So that's another thing, right? If you're turning it, there's a point where it should stop, right? And so then it's another indication that that valve's no good. But anyways, that table, that data that's generated should always be compared against what the manufacturer recommendations are. And there's a range, right? We don't know all manufacturers, and we don't know what's going to be buried under there, but you'll get a feel for it over time. Unfortunately, like I said, I don't. Yeah, so let's see, who's Mueller? Stan Pachorik here in the Valley. You can probably talk with Corin Maine, and that they probably have somebody. That's who let me borrow their valve, is Corin Maine. So yeah, you'll have to go through there to figure out the torque requirements on the operator nut. Let's see. Cast iron, like I said, so cast iron is what we had forever and ever, and it's what the original metal seated valves were. We got ductile iron in the 70s. We started having resilient seat valves, and so the key takeaway there is ductile iron is going to be a more robust. You'll start following the 515 standard, and which means, and that they'll call it like a thin wall valve. So it doesn't mean that it's less strength for 515. It just means that we're using a stronger material. So they're trying to lighten the valve, use less material, and make it a little bit cheaper as compared to the what did I say, the 509 or 504 or 509 for the full thickness valves, but that's based on cast iron. Epoxy coatings. How many know what holiday free means? Or what's a holiday in the painting world? It's where the painter took off and had a holiday, right? So they missed a spot. Yep. So, you know, you spend a lot of money on these valves. You plan on putting them in the ground. You want to try and just go the extra step. You can ask for your valves to be coated and holiday free, which means that they'll probably put a little bit thicker coating on it, and they'll do a spark test on it to make sure that the valve is 100% encapsulated. I forget off the top of my head kind of how many mils are lost every 10 years. I'll have to talk to someone that knows more than me, but there is an actual degrade over time. But again, you know, try to get as much life out of your valve as you can. So I try to push for, and you will pay for it, right? But you know, getting a holiday-free valve. Epoxy coating is great for underground. Epoxy is not great for above ground, especially if you're in. Well, I mean, it works above ground, but it's not going to be great for like if your pump station has a public setting and there's an aesthetic. You know, as an engineer, I don't care. Like I think, you know, big fancy equipment's cool enough for me. I don't care, you know, if it's painted blue, purple, or what. But epoxy will actually create a chalk layer over time. You know, sun degrades it a little bit. So if you do have an exposed valve, make sure that it gets coated with like a polyurethane or something else that has a little bit better UV performance if you're in the public eye a little bit more. 304 versus 316 hardware again. So this is talking just about like the bonnet bolts and the flange bolts and things like that. 304 I think is okay for above ground. 316 is going to be your more robust or your more corrosion resistant material. And so you'll want to, so I prefer it in a buried application. All right, so design question. How often should we have a shutoff valve in our system? What's your guys' rules of thumbs? Every 500 feet, every 25 customers? What the city is willing to pay for? Yeah. So a shutoff valve, right? If you have just like a straight long run, you know, I have a pipeline that runs from a treatment plant to their infiltration basin, no connections anywhere in between, but I have 10 valves for like 3 miles, 2 miles. I'm not serving anybody. Why do I need a valve? Right. And so, but the idea is that, well, if this pipeline breaks, you know, then you're going to, you know, have all that water going out. I can probably tell you by the time you get there and shut off one of the valves, it's probably going to be all drained anyways. So, you know, engineers and their common sense, I tell you what, problem. But there is some kind of ideas that might be more, especially when you have branches and T's and services. Again, you'll work with your agency and figure out, well, okay, what is an appropriate number of customers to be out of service if I have a line break within this community? I've seen anywhere from 20 to 50 people. You know, it just depends on what you're willing to say in there. Transmission lines, you just trying to control, you might need to control or shut off a portion to maintain that section. You know, maybe at some point that line that I was telling you about, they might want to put a tap on it and feed one of the nearby industrial plants or something with it. So, you know, it can serve a future purpose, but, you know, you can get if somebody wants to put in a tap for the water, you can probably make them pay for the valve insertion as well. Nobody cares about water until it's not there, right? I probably shouldn't say that in a public forum, but you know, again, it's you all are very, very important individuals to the community, and educating people is part of it. And I think it's very important that we, you know, we try to be kind and educate wherever we can, but helping them understand, you know, there's certain things that need to make sure that you have clean, reliable water on a consistent basis. All right, so installation ideas. If you are ever, we sometimes as operators, I say we like I'm part of you guys, just hoping. I'm just, like I said, I want to be like you. That sometimes we wear different hats as we go through our careers. Sometimes we're simply the operator, sometimes we're the plan reviewer, sometimes we're the construction inspector, right? So when it comes to installation, inspection is a very, very important part of the job. Or make sure that you tell your construction manager what you want to look for. These are some of the ideas. One, make sure that when the valve comes on site that you're going to, you look at it. So let's list off a couple of items. What do you think we should be looking for when a valve comes on site? Right, any damage, definitely look for damage. And this can be anything. It can be the coatings damage. Again, if you spend the money for a holiday free coating, you best well get a holiday free coating. You know, it doesn't need to have chips, scratches, or other parts missing. So you look for damage, make sure it's the right size, right? What else can we do? right? If you do have a controller, I didn't cover controllers in this, but that being, or yeah. So if it's a control, are you talking about for a control valve, or are you talking about the operator? The operator, okay. So there's different types of operators out there, right? There's hydraulic, there's electro-hydraulic, there's pneumatic, there's electric. Did I say pneumatic? Yeah, so air, hydraulics, and electric, or some kind of combination of them. That it's what you specified, make sure that that's all together, it's orientated correctly. You know, operators can be a whole different beast, because you can have remote mounts, you can have them all together, you can have funky, you know, left facing, right facing, upside down. I just want to make sure that I can read the indicators at the end of the day. So take a moment to look at those kind of things. If there is a direction to your valve, make sure you work with your installer that, hey, I see the arrow, this is the way it's going to go, plan ahead, think about that, make sure that that's put in there. So you're getting ready to get it installed, and you go in the hole. What are some of the things we should do before we actually slide it on, or we put it into place, right? Go through this process, think in your head, okay, if I'm breaking open my line and I want to make sure that I'm as efficient as possible, I want to ensure that I get as little debris into the pipe, right? Because that means that if we get dirt in there, then that means it's got to get flushed. It may mean that we have more contamination, that we have to increase our chlorine to disinfect it. If we don't pass our back tees because we have a lot of debris in there, we got to flush it again. So anyways, it's a time thing. So some simple things that we can do is we can just simply close the valve, right? As we're installing it, make sure we clean it out. Like if you look at that valve, it's been sitting in the warehouse for I don't know how long, but it's collected dust. There's actually some grit in it. So make sure that that gets wiped out, cleaned out. And then, like I said, close the valve so that after it's on, you're not going to be kicking dirt into the pipe or what have you, and making sure that you're being as efficient in your process as you possibly can. There are, like I said, there are standards out there that talk about how the valve is going to be put in. This comes from MAG. Their detail for installing a gate valve or a butterfly valve. We talked about restraints a little bit. Is this valve restrained because it has a concrete block underneath it? Let me think. Yes, no. Yes, no. No. No's correct. No's have it. And that's right. This is nothing more than a support, right? For this valve to be restrained, you're either going to need one of those restrain collars, or you're going to have to have it be flanged or some other device. Let's see, same idea. You can see it even more so with the butterfly valve, right? It's showing the butterfly valve turned on its side, and that's how I'd prefer it to have. The reason being is that I don't like my bottom yoke to be where debris can catch and build up. So having it on the side is just one step a little bit better. So following the standards, make sure that they're looked at. I was appreciative for Chris McDonald when he said, hey, talk with the manufacturer about pipe installation. Talk to the manufacturer about valve installation. Make sure everybody's on board, that we're not going to void any warranties, and that it's going to be a successful thing. It's not too complicated, but you know, just checking the boxes, making sure we're all on in the same direction, I think is always an important thing. Let's see. When we're installing valves, something I wanted to talk about after bolting patterns here. Bolting patterns, what kind of pattern do we use to connect up a flange? We go clockwise, counterclockwise, crisscross applesauce, star pattern. Yeah, you might hear it as some different, but zigzag kind of pattern, right? We start one, go over. I forget what I forget the term that they used in the manual. I'll have to look it up again, but yeah, you're not going around in a circle pattern because you're going to put differential forces on your gasket. You'll pinch up here really tight and it'll be really loose down on the bottom. So if you do your star pattern, I don't know if you've ever done a head gasket before, but same kind of idea as your heads, right? You distribute your bolt pattern tightening to make sure you get an even closure and force across your gasket to make it sealed. Does the same thing hold for mechanical joints? Anybody done a mechanical joint? Can you just go around in a circle on a mechanical ring? So the restraining lug is torqued off, right? But for the gasket, can you start just at one, hit your torque point, and then move right to the next one? Or do you have to do top lug or top nut, bottom nut kind of thing? You still have to go through, right? You don't want it, again, you want to create an even sealing surface or force against that. So that's an O-ring, right, that we're wedging into the valve or into the fitting, right? You don't want to, over tighten one, because if you wedge one in, this one's out here, it's going to be trying to push itself out, right? Cantilever itself out. So anyways, cross-contamination, something I wanted to bring about, let's see, I forget. So cross-contamination is actually a state regulated law, right? That we can't create conditions that endanger our water system pipes, either because there's a fitting too close or that we're within a zone of influence with a wastewater pipe or some other non-potable water source. So if we're putting in valves, we have to replace valves, make sure, it's a good idea to think about, okay, is there a wastewater line here? What proximity is it? Am I going to create a problem with a cross contamination? So just be aware, again, there's standards, the MAG standards have illustrated them pretty well. You can go look at those. And you know what, I'm just keep on talking here. I didn't even know whether I was done. Jeez, I wasn't even. All right, man. Yeah, I was going to go through control valves. I was going to go through air relief valves. So I'm happy to give people more information whenever they want it. But last kill off here, post installation. After something's done, good, accurate record drawings. Nothing's worse than when you have a bad set of drawings that the contractor didn't update and you're searching for a valve for the next 10 years until it breaks or something, right? Make sure you understand your O&Ms and your standard operating procedures. And I highly recommend enforcing an asset management program. AWWA had a really good introduction into an asset management program. There's a lot other places through like Water Environment Federation that also have asset management training and things like that. But again, the improvements that drinking water has had in our lives, I think we owe it to make sure that these systems are maintained to keep that level that's improved our lives as well. So with that, thank you. Let me know if you have any questions. If you put it to the very last slide, it has my contact information. You're welcome to call me, ask me questions. Come join the water distribution committee with me. Happy to have you and coordinate from there. Anyways, thanks.
Thank you, Dane, very much. So at this point, we're going to go ahead and take another 5-minute break in case anyone needs to go use a restroom or take get a quick drink of water. We're going to have our next presenter up from Hydra-Stop. Within the next 5 minutes, we're going to get him set up and then we'll start it up. Also, if you need any questions or if you need a business card from Dane, please go ahead and visit him at the table in the back.
So, oh, okay. All right. I think I used to call him Welton a little bit too, my previous life. So,
All right, everyone, let's continue with our last and final presentation of the evening. Just as a reminder, in case anyone needs to step out, all these presentations will be available. Just be sure to reach out to each presenter and they can go over any information or any additional questions. So without further ado, we have Michael Irwin from Hydra-Stop.
good afternoon, everybody. Okay, perfect. Everybody can hear me. Good afternoon, guys. My name is Michael Irwin. I am based here in Tempe, Arizona, and I am the West Coast regional sales guy for Hydra-Stop insertion valves. All right. First question of the day is, who here does their own tapping by a way of hands? Does anyone tap themselves? Tapping, yes. What city are you from? Oh, San Luis, okay. How high do you go up to? Do you go up to 12-inch for your own tapping? 10, okay, excellent. Tapping is something that we're going to kind of talk about a little bit, but I'm going to get into my whole, the overview of my presentation is about insertion valves, but you can only get access into a pressure vessel by tapping. So if you've ever thought about tapping or tapping into a line and having that capabilities, there's a lot of synergies involved in that when you're doing it, but we'll get into a little bit. The topic of my conversation today is valve insertion. Let's see if I can hit it there. Alrighty. Not working. Next slide. All right, we'll work it that way. I'll just click the button and go from there. So why am I here today? For the first time in American history, the current administration has been funding drinkable water infrastructure. As of March 8th, 2022, $50 billion has been put towards drinkable water infrastructure. There is nothing more important than water. Okay, I got into this industry in 2019. I used to work for General Electric. I did big pressure relief valves for like Palo Verde and for APS and SRP. But I saw this opportunity of an insertion valve that can go into a drinkable water system, and I'm like, sign me up. Because I really truly believe that the water industry is going to be the biggest industry in the next 7 to 15 years, especially in the Southwest United States. So this right here, you know, the first largest investment in American drinking water systems, that's excellent. This right here is a picture of just the things that you have to deal with. This is in New York, a lot of what's underneath your feet. This is California, hashtag save water, water conservation. and I do a lot of that stuff throughout the Southwest. So who am I? Like I said, Michael Irwin. I'm based in Tempe, Arizona. I cover the whole Western United States. Been working in the water industry since 2019. I've been through 2 insertion valve companies, okay, just to kind of give you a little history and a little bit of background. But the biggest thing, the only thing we really need to survive in this world is water and time. Those are our 2 most precious resources. Some of the things why water's been so important, I don't know if everybody remembers a couple of years back, there was that contamination issue in Florida. Okay, water's important. Not being able to have that critical resource when needed, it's super important. Jackson, Mississippi this year had they were without their water system for about 2 weeks, just chaos, and it really shut down the whole town. You know, we see it every day. You guys see it every day. You'll see mainline breaks as aging infrastructure comes in. You know, we had a little thing called COVID. Okay, how do you cure COVID? You wash your hands. You weren't allowed to shut any customers off. It was the best thing in order to do to prevent COVID was bathe, wash your hands, don't spread the disease. I do a lot of work with the California Water Boards. We do a lot of CEU credit. So if there's ever a time here in the state of Arizona where you want me to come in and educate some of your local guys there too, just feel free to let me know. I do a lot of breakfast and learns all around the West Coast. So if you're on LinkedIn, love to connect with you. Feel free to let me know. Thank you guys for setting this up. This is absolutely awesome to come in and actually visit with you guys in a nice controlled environment where we're just sharing data and we're sharing information. So thanks again for doing this, and looking forward to presenting. So why am I here? What is our business? In the United States. Must have hit that button there. Okay. We are the largest line stop and valve manufacturer in the United States, and we work with thousands of municipalities around the United States. Why do we exist? We exist because 20 to 50% of the valves in America's drinking water system, they're no longer working. They're inoperable. They might not be there. It's just aging infrastructure. And water is the great equalizer. As you know, water will win every time. So, you know, what an insertion valve is we're able to, we know why we exist. We know why there's problems out there. We know why we don't have additional control points due to the infrastructure of aging. So what we've done is we've created a line stop and valve insertion solution. And this is all we do. We do this because our whole goal in life is to avoid a water shutdown. So our product is specifically designed to avoid a water shutdown, and that's insertion valves as we go into it. Let me see here. This is a quick little video in regards to why we exist. Okay. It's got no voice on there. I can't see it, but do you know that 30 to 50% of valves in America's drinking water system are inoperable, not existent, or not there? So if you look at it, you look at everyday USA, you might have some issues where you have to replace a valve, you want to avoid a water shutdown. These are all the things that you guys face every day. I can go ahead and I can incorporate an insertion valve in without shutting down the system, without shutting down schools, without shutting down factories. You know, critical locations where you need water to be running, we've created this insertion valve product. I'm not sure why it's not doing that, but I'll let that run out through. Okay, so I can install a valve under pressure in about 45 minutes. We work with a couple different companies here in the state of Arizona. We work with Bruce Martell over at Pipeline Services, and we also work with Don Harden and Steve Helm over there at Tapmaster. Just a really great solution, which I'll get into. The InstaValve is our brand. Hydra-Stop is our product. There we are. So get to know us. That's another overview video on my product here. I don't think I can see the sound there. Let's see if the sound's working. What's that? Oh, there it is. And let's hit play. Can anybody hear that?
At Hydra-Stop, we're on a mission to provide solutions for control to make the world safer, healthier, and more productive. And we accomplish this with a keen focus on service.
For providing solutions that eliminate shutdown during plant, routine, or emergency maintenance, to developing relationships with utilities, municipalities, contractors, and engineers. Service is at the heart of our business.
Manufactured and shipped from our facility outside of Chicago, our solutions allow the ability to maintain and repair portable water, wastewater, without service disruption to communities around the world.
Hydra-Stop's team of engineers are continuously innovating and creating solutions that provide the reliable and affordable service our customers depend on. Solutions that reduce costs and risks while ensuring more maintenance.
I have a lot of
or ensuring your crews are properly trained.
All right. I have a lot of videos on my presentation, but it didn't quite go through over the deal. We do have that on our website, which I'll share with you guys. My business card's over there at the very end. But kind of starting over, Hydra-Stop insertion valves can be used on any different types of application. We do a lot on asbestos AC pipe, cast and ductile iron, PVC, and steel. If I know what the outside diameter is of a pipe and I know what type of pipe it is, then I have an insertion valve that I can go ahead and put on there. So just understand that concept that we work on all different types of pipe. What are the feature benefits about using an insertion valve or have that ability to put a valve in the ground completely under pressure? There is an additional savings if you look at it. You know, I'm able to come in, do a 5x5 excavation, and I'm able to put in a resilient seated wedge gate valve in the location you want, in the time frame that you want, you know, without shutting any customers off. So that being said, that's a pretty good savings or a dollarization factor when you really think about it. We're eliminating all the costs involved of boiling water notices, different things like that. Those are all things we're looking to avoid. The next part about it is control. You know, imagine being able to regain a control point where you didn't have one before. That's pretty significant when you look at it. You have a broken valve and you don't want to have this huge area to shut down. We can go ahead and we can add it, like I said, reduces time, efficiencies, and gives you those control points of where you need it. Environmentally, you don't want to lose pre-treated water, especially in our current climate where water conservation is the biggest focus. That's the biggest thing you want to do is you don't want to have contamination, you don't want to have a disruption, and you don't want to lose pre-treated water. Last part is safety, all about working smarter, not harder, working with all your efficiencies intact and everybody able to do it. You don't want to lose fire protection. You don't want to lose that safety features. You don't want to have people, you know, draining in a hole that's got water going around. I've seen videos everywhere, you know, using saws and everything like that. Those are all the things that we're trying to avoid. All right, so here's our company. I mentioned tapping in the very beginning because we first started out by manufacturing our own tapping equipment. And if you tap yourself, there's a lot of synergies involved with that. There's a lot of way to make money or save money. Take a step back. Best way to make money is to save money. If you're doing it yourself, if you're maximizing your own efficiencies and maximizing your own staff, then you're saving a lot of money. Tapping is how we first started. We first manufactured our own tapping equipment, and then we first incorporated the insertion valve and line stopping. As we've progressed, we've kind of made it and made it into a product where we offer a 4-inch up to 24-inch solution right now. So a number of different processes that we've got. You're able to tap, you're able to have video to where you can go in and see if there's FOD or if there's an illegal tie-in to your lines or anything like that. Everything that we're doing with insertion valves is able to gain access to your water distribution system. Back over this one. Put that there. So at Hydra-Stop, we've got a great kind of a digital pathway in how we kind of educate our customers on what our solution is and what it does. We've got testimonials like crazy where we've helped avoid a water shutdown. We're able to add the additional control points. We're able to do it on more of a smarter and efficient time in order to maximize all that efficiency. So this is all we kind of focus on. We focus on line tapping, where we manufacture and make the line tapping equipment. We also do a line stop. Who's all used a line stop before? Show of hands. Anybody? Okay. A line stop is a temporary line stop. We can go in. A couple months ago, it was on Mother's Day, City of Tempe called and said, hey, do you happen to have a 24-inch valve I could put on here? They had a big problem. I don't know if you heard about it. It went underneath I-60 and McClintock. What they did there, it was concrete cylinder line pipe. And what they were able to do is they were able to put a line stop on one side of McClintock on the north side, and a line stop on one side of McClintock on the south side. So what they were able to do is they were create a line stop and flow and stop the flow of water. Doing that, it was a temporary solution. And as lines, go ahead. Oh, sorry, you're stretching. I thought you were asking a question. But with line stopping, like I said, it's a temporary fix. You're able to come in and stop a line in a temporary setting. And as we've progressed as a company, we've created, instead of just a line stop, let's have a permanent asset in there. Let's have a valve insertion. Let's have a workable valve rated for 250 PSI that you can add to your system and actually add to your valve auditing program. That's one thing we've kind of designed in. How do I turn this off here? The feedback. Yeah, I'm trying to figure out now my computer. A way to turn that back. We'll turn that down. Yeah. There it goes. I'm repeating myself. Perfect. Sorry. Okay, so like I said, our focus, line tapping, line stopping, valve insertion, and we focus on the education and support. So this is all we do. This is all we're focused on. This is our continuous enhancement. This is our only product line, and this is what we're good at. So that being said, what are some of the impacts and challenges that you guys have to face when you're doing a shutdown within your community? You've got a system pressure drop. These are all the things we want to avoid. You don't want to put large portions of your community out of water. You don't want to issue boiling water notices. You don't want to have the liability of not having fire protection. You don't want to have that loss of water revenue. Those are all the community impacts that your guys are going to face. The work challenges is, it's underneath the ground, it's excavation, it's redoing all those steps in order to get to it, determining which valves are working, which ones are not, how big or how much liability do I have in my shutdown. There's labor costs, there's material costs, all that stuff kind of adds up as an impact of what your shutdown is. So if you start thinking about it in the insertion valve, it's a better way to solve the problem. So these are the 5 manufacturers that are currently in the market with insertion valves. AVT, Advanced Valve Technologies, is the first one I worked for. I didn't have a lot of success there, but when I stopped working with them, I tried to figure out, and I saw it after Hydra-Stop. I said, okay, guys, who's getting it right? Who's the best in valve insertion? And that's what brought me to Hydra-Stop. We do the traditional tap, where we tap into the line here, and it comes down this way. Also, Mueller and team, Mueller just recently got into the valve insertion world too, where they do a complete cut-in valve. It's a different process, it's a different cost structure, but when the biggest company in the land in the waterworks world has gotten into your space, you're doing something right. You're solving a great problem. So what we've got to, like I said, I wanted to show this competitive nature because this is how people gain access to the system. With AVT, it's almost like a slot and a cut where you have to get into it. We use that traditional tapping method because if you're following the procedure, you're following the stack, it's all reliable and repeatable. And Mueller and team, they have an actual cut-in valve, which is a bigger job. It's a bigger exploration, but it's just a different methodology in order to gain access to a pressure vessel system, which is the water distribution system. So, like I said, traditional tapping method, we create that. We manufacture it all in Chicago, and we gain access through the system through a temporary knife gate right here. So you've got the ability to come in and tap, gain access, and have all of that security and no contamination to gain access to your pipe, where we can come out, we can pull out a coupon, we can take a look at the integrity of your system, we can take a look, do you have tuberculation, do you not have tuberculation, what's the consistency of the water? These are all the ways we can kind of gain access to that tapping procedure. So introducing yourself to an InstaValve. Right now we have a solution of 4 inches up to 24 inches. Like I said, we work on all different types of pipe, AC, ductile cast, PVC, you name it. If we and once I said, if we know the outside diameter and we know what type of pipe it is, then we have a recipe in order to go ahead and fix it. Okay? What are some of the key features of using an InstaValve or being able to put in an insertion valve? You know, we have a line pressure where we work at 250 psi, and it eliminates 100% of a shutdown and all the costs that are related to it. We have a certain method where we gain access to AC. This is a permanent asset, 3 turns per inch, like AWWA standards, stainless steel construction, and it's only a single tap needed. The reason why we know this is the company that we work with. They've done everything, and they've done the proof of design standards to meet and exceed all of the AWWA C509 and C515 resilient seated wedge gate. So that being said, I'm going to go into it a little bit more, but this is kind of a cutout or an outline of our area. Basically what it is, it's a JCM fitting here, which I'm sure you guys have used and you guys have installed and you know the process behind it. And then it's a bonnet with a resilient seated wedge gate in the inside. So that's what an insertion valve is out of that material. So the InstaValve 250, we test everything. We tested at 375, our working pressure is 250. We have two ways we perform it. We have an AIS standard and then a non-AIS. So a lot of the projects that are coming out right now, they're requiring AIS, American Iron and Steel. We just did a project yesterday where we installed a 16-inch up in China Lake over in California, but we meet all the requirements for Buy American. So I just wanted to make you guys aware of that. All the classifications you need to be installed within the drinkable water system, 61 and 372. We meet this. We are UL approved, and we're the only actually insertion valve that is UL approved, United Laboratory Standard. So getting into that more, this is how the process starts. So what we do is, like, we're going to go ahead and we're going to mount a fitting like you normally would. We're going to go ahead and mount a fitting, and then before we even tap, before we even gain access to your pressurized system and open it up, we're going to go ahead and do a pressure test. Everybody varies. I think the city of Phoenix wants 45 minutes at 1.5 times the line pressure. City of Las Vegas requires 200 psi at 2 hours to hold the pressure. But whatever you need, the first process of incorporating it is doing a pressure test. That's to make sure that the fitting is go ahead and can take the pressure and can add it to your system and become an asset for you. The next step, what we do is we basically perform a tap where we use a temporary knife gate and we'll gain access, opening and closing your system through the bonnet, through the wedge, through the valve here, tapping, coming down. The next part of the process, where we put that plug, operating valve into the system. And at the very end, you've got an operating workable valve set for 250 psi. The InstaValve 250, there's kind of the breakdown of it. So this is what we're trying to avoid. This was in Tempe, actually just south of me on Guadalupe and rural. This went on for a number of different days. You could just see the more and more they tried to fix it, the more and more the problem got bigger. Every time they went out and tried to get a good shutdown, it's like, well, that valve doesn't work. Okay, I got to go out further. Well, that didn't work. I had to go out further and further. And that's the thing is, though, that's why water is so important. And the job is tougher than most people realize, you know, because it's just, water's a great equalizer and it'll win, especially here in the desert when the heat and everything like that. So, but this is all what we're trying to avoid, this uncontrollable water shutdown where you're putting customers out of water, where you have these roadblocks and these issues, because that can add up like crazy. This is our guys out in California, City of Ventura, kind of does this themselves. We've got a lot of cities around the United States that will do this and incorporate the valves themselves. City of Portland, we just did Los Angeles, Houston, New York, all this stuff. They work on this and they do this themselves because they can incorporate when they need a valve. They work it as almost like a preventive maintenance program. So that being said, that's kind of what we do. It's kind of how we are. This one right here is, so I got a call during COVID As you can see, everybody's wearing masks. I got a call from the Sheraton hotel, and they said, hey, well, it was actually LADWP started it. Sheraton was involved. So we got a call from LA. They said, hey, I've got a 12-inch main line that's running right at LAX, right at One World Way, you know, right going down the line, right into the main drag, an area that they can't shut down. And they knew they had a 12-inch cast iron pipe there that had pitting, and it was just deteriorating and corrosion. So they knew they needed to get it replaced. So on this side of the street, we had the Sheraton Hyatt House, and there are 300 rooms. Obviously, that didn't want to get shut down. On the other side of the street, we had United Airlines with the airport, and obviously you can't shut down an airport, especially a busy international airport. You don't want to shut down. So what we were able to do is we were able to work with LADWP. They were able to look at our valve. They were able to approve our valve. In the morning, our contractor was able to come in, install our solution in about 45 minutes on one side. In the afternoon, went to the other side and installed it. Then when LADWP, when the airport wasn't busy, when they had the pipe there, when they had the construction crews, when they had all of their synergies in place and all of their positive things in place in order to do it, they replaced the line on like a Tuesday evening. But they were able to do it themselves. They were able to shut down the water without shutting down the Sheraton Hotel. They were able to do that without shutting down United Airlines at LAX. I mean, the cost structure in order to do that was massive. But that's one of the solutions of what an insertion valve can do. Putting a valve in when you need it, where you need it, how you need it, on your time frame, with all your synergies in place. That's really what the solution of insertion valve is. So that being said, 2024 Olympics, you know, that's what everything around LAX was getting beat up there and getting kind of redone, because God forbid if that happened during the Olympics. You think of the delays, you think of the cost structure, everything like that. It just would have been outrageous. But there's just a testimonial, and I've got thousands and thousands of testimonials on how insertion valves help out and how insertion valves kind of solve a bigger problem that are out there. So with the focus today, and I know you guys have been in here all day in a lot of trainings, just know that there's an insertion valve out there, or there's a technology out there of insertion valves where you can incorporate it, add it, and avoid a lot of drama and avoid a lot of issues. So that was just one of the testimonials that we had. Any questions or anything? Great question, because every single pipe and will have a different recipe to it. AC 150 has a different recipe. AC 200, different recipe, a different material. As long as I know what it is, then I can match up the recipe of what's needed. Because let's just say, let me do this way. Let's just say that was an AC 200 line. Okay, that means that inner diameter is a lot not as great as like a normal. So what I do is I have an undersized cartridge that I can use up. As long as I know the data, and as long as I have that data beforehand, I can incorporate a valve in there, and it can be an operable, resiliency to wedge gate valve at 3 turns per inch. No, we seat against the pipe. You know, where other valves kind of seat against themselves, which is a bigger, like, so tuberculation. Let's just say you have tuberculation in the pipe. The more you operate that valve, the better off that smooth surface is going to be. So it works really good on tuberculation, our solution. Because it's a really, which I'll show you, it's a resiliency to wedge gate that goes down and basically compresses, and then compresses out at the 3 and 9 o'clock position. So if I know what the outside diameter is, then I'm matching up my inside diameter, because I no AC pipe is perfect, but ductile, cast, steel, you can get pretty close on what they're doing. And as long as I can get close, then my number of turns and my method will seal that pipe. And we guarantee a workable shutdown on ours, which I'll show you some pictures on. Does that answer your question? So that being said, we were able to go ahead and put in 2 insertion valves for LADWP. And like I said, they were able to use all of their efficiencies in place. They were able to shut down the line on their time, and they didn't put any customers out of water. the Sheraton was able to maintain their revenue with their 300-room hotel, and LAX was able to do what LAX does, and United Airlines, they all stayed in service. So we avoided a bigger problem just by using the insertion valve. So what type of market application are we looking at? Why would you use an insertion valve? So let's just say this is Phoenix, this is Tempe, this is San Luis, this is Yuma. You know, you've got workable valves, and then you've got non-workable valves. You've got businesses, you've got schools, you've got all these things that are that rely on the water system that you're providing. Boom, let's just say there's a water main break right there. Based on the efficiencies of what's working and what's not working, you have a huge coverage area. Okay, I've got to affect the school. I've got to affect the hospital. These are all the things that you want to avoid. So if you can think about it, and you can go ahead and say, you know, predictable maintenance, predictable planning, or using a contractor that stocks these, which both of them do here in Arizona, I can go ahead and I can call out an emergency service, and I can put in an insertion valve and only affect a limited number of people by using that technology, knowing that, you know, where your liabilities concerns are here and here, be able to incorporate a valve where you want, when you want, how you want it, with everything in place. So that being said, you know, the more and more as it comes down, you know, and the more and more of funding comes towards these drinkable water systems, look at improving your technology. I'm working with Lisa up at the city of Clarksdale about getting her systems ready to go. She's got so many inoperable valves that are out there, but we're working on the process of being able to, hey, I got a broken valve, incorporate an insertion valve. Hey, I've got a broken valve over here, and just kind of make her system better. And it's a long process. It's going to be a 5 to 7 year process in order to do it, but it's just a better solution, more efficient, more time. This right here is another video. I'm going to play it. I'm going to kind of talk through it. Hopefully I don't want it to go through. This is our installation process on how we do it. We'll mount it up, and just like a JCM fitting, we've got torque ratios. We've got a procedure that we follow. We'll go ahead and add our temporary knife gate on there, gaining access and no contamination. There we are tapping, and this right here is getting our pill cartridge or our bullet ready. And what we do is each one's got, like I said, got a different recipe, a check valve in order, if we are going to put it into a pressurized system that's 225, we don't want to be slamming that thing in. So we've got a check valve, or we can kind of ease it into the system and add it in a non-aggressive manner to the water distribution line. This is our housing, which we just did one of these for Scottsdale a couple days ago. And we do hundreds a day, so it's kind of all over the place. But with this being able to come in, everything's got a process, everything's got a procedure, where we'll come in, we'll open up a temporary knife gate, we'll be able to add our pill, cartridge, or bullets into the housing. And then when we're ready, we can go ahead and operate the valve, close the valve, and create that close when needed on your time frame with all your efficiencies in place. So that's just kind of a review. This is also online, some of our things, and my business cards back there too. But it's a real simple solution. Is about 16 different steps when you're going to go do it, but you know, 3 turns per inch like the AWWA standards, and you know, you get that compression point here at that 3 and 9 o'clock position. So that's the insertion valve. Next slide here. All right, like I said, the traditional tapping method, it's just reliable and repeatable. It's been around for 100 years. That's kind of why we've gravitated towards that. Heavily tuberculated lines. You know, if you can go in and you can pull out a coupon and say, yeah, okay, I've got 2 inches of tuberculation on a 12-inch line, then that's going to affect your number of turns. The gentleman earlier was asking about, you know, torque ratio and how much torque do you need in order to close a valve. You know, ours turn by hand. We do have a process. As long as you count the number of turns, then we're good to go. That's all we require, which I'll show you a couple other things too. So you can see, if you do have 2 inches of tuberculation on a 12-inch line, you're gonna do 30 turns, not the additional ones, because you want to be able to break up that tuberculation. So deconstructing the insertion valve, kind of why we make ours the way we do, you know, why most companies do. operating nut, open left, open right, all those standardized things that you have. Everything, all of our body is a 304 stainless steel. Like I said, all American made, and we have an AIS and a non-AIS solution available. Epoxy coated valve bonnet. Everything is designed to work in sequence. You've got upper and lower gaskets. You've got the completion rug, completion plug here. And like I said, everything is designed to work in sequence with the fitting. The bullet and the fitting work in sequence. The engineering is phenomenal on it. And this is your resiliency to wedge gate. So as you come down and you press, we're going to get a fan out at that 3 and 9 o'clock position. And that's the AWWA resiliency to wedge gate standard. Wipe seal, almost like a wine cork as you're going down and up, increasing and decreasing your pressure. There's our resiliency to wedge gate. We make everything a certain way. It's almost like that memory foam where it'll come and bounce back. It's got mesh layers, rubber layers, all incorporated, like I said, in order to get the compression, lock out at the 3 and 9 o'clock, and then be recoiled back to go back into the valve bonnet, as you can see there. Real simple, completion plug, stem collar, no brass, conforms to NF 372. Check valve for the pressurizing, being able to put it into the system there. 1.5 inch, 2 inch stainless steel valve stem. These things are not deteriorating. They're not busting out on you. You're not going to break it even if you put 425 pounds of foot torque on it when you're going to go ahead and open and close it. We've actually broken our valve turning machine. You know, you're not breaking this thing. It's a testament to kind of how they've made it, you know, and how insertion valves have kind of, they are becoming standardized. Really, the quality behind how they're making in the manufacturing process has been great. So diameter of the stem, all the working pressure, 370 or 250, test everything to 375, all made in the USA, meets the iron and steel like we talked about, meets all the classifications, convertible to a line stop if needed. So how do we know this? How does the company know this? They've tested everything, and that's one of the reasons that kind of drew me to Hydra-Stop when I got involved in the insertion valve world, because I think it is such a great solution. You know, if you think about it, you're able to put a pipe in the ground at your time, at your schedule for a fixed operating cost, and you're able to solve everything else behind the line. You know, that's amazing. We know this because they've done a proof of design standard for C509 and 515 is the testing that they've done. There's a hydrostatic gate test, there's a torque test, a leak test, and a shell test. The gate test represents like a water hammer. And what we've done is we've tested it against that. The requirement was to be tested at 500 PSI for 5 minutes. We took it up to 550, tested the same procedure. No issues, no damage, no worries when it came down to our resiliency to wedge gate. So we exceeded the standard on the water hammer. The next one was the torque test, which is that stem. You know, the requirement was 350 foot-pounds of torque. We tested it at 400, no issues, no damage. We've actually tested it up to almost 750, and we haven't broken the stem on that program. So as you can see that run down, no issues, no problems on the torque test. So we exceed the value there. The next one is a leak test, and that's when we will do the leak test before we even tap into the system. We'll test it at every 25 cycles. You know, no damage, no issues, no problems when it came in there for the leak test. The more you work the resiliency to wedge gate, the better off it is what we found in our data. So last part is that hydrostatic shell testing. And that was basically the outside of the shell. The requirement was 625. We took it up to 700, way above that. There's no issues, no problems. Meets all the shell testing for that requirement. So at the very end, it shows, hey, So what we do is we guarantee a workable shutdown when you're using an insertion valve. Here's our insertion valve here. There's considered a shutdown before, but that's our workable shutdown. We got a different process there. Tuberculated lines, when you're doing a hydrant replacement and you want to be able to regain a control point, you can add an insertion valve to your system. There's just more pictures. You can see it on a heavily tuberculated line. All right, this is applications out in Molten Nagel where we're working on PVC, but you can see they're wrapping the valves at the end, but real nice tight seal on it, 3 turns per inch. You're good to go. Cast iron, you can see there too. Be able to put in insertion valves on it. Horizontal, you know, some low-level situations where you, we did one of these up in Buellton, California, where it's an older downtown and everything's buried super low. So what we're able to do is you're able to put it on a side, you're able to side tap it and then mount it on its side. And then we have a beveled gearing that you can go ahead and do it. So you can mount it horizontally. We did one of those up at Las Vegas Valley Water with a 24-inch where we actually mounted it on its side, which I've got a product testimonial on that too, if anybody needs to look at it. So vertical, horizontal on an angle, whatever's needed, you can go ahead and kind of put the valve in. So it gives you a lot of autonomy in regards to managing your own system, managing your own distribution. You know, you put the valve in where you need it, how you need it, when you need it. So multiple buried lines, say you have a sewer line next to it, whatever, you know, you're able to put that in. You just have to move your valve box. All right, backfilling procedures. We, on our 4 through 12, we just require you guys to barricade underneath of it and then do your backfilling procedure, but we rely on the municipality for whatever codes and standards that you want to do. On our larger diameter stuff, we do require to pour in concrete before operating, which I'll show you, but one of the solutions we've got there. So it just kind of shows the versatility. Like I said, you're able to put in a valve and operate it where you need it, when you need it, how you want it. So, you know, why look at an insertion valve or why get have the knowledge about it? You know, you're all here to avoid a shutdown. It's all at the small excavation site, easily installed in about 45 minutes, very tight spaces, exceeds the AWWA standards. You know, and in today's environment, the last thing you want to do is have a water shutdown and have water running down the street. Water conservation is so big, so you definitely want to kind of follow those systems. All right, this is, we also have a 14 and a 16, same exact material, just a little bit different engineering behind it. But you can kind of see that there is, we had a 16 go in, like I said, at China Lake the other day. Great system, shut it down. The 20 and 24, we've actually done some of these out in Buckeye, Arizona. We did one at SeaTech. We've got a couple more going on in Hawaii, Q1 of next year, but great system. I got a couple pictures of the one we did here in Buckeye. But we're able to put a 24-inch valve in about 4 hours. I mean, if you look at it, your small excavation site, you're looking at the component driven, how it is, but you're able to do that, incorporate it, and shut down the line where needed. And it's a big valve, but it's the same concept. Temporary knife gate. Opening and closing, temporary knife gate, tapping, gaining access, all that stuff, following the procedures of torquing and everything like that. So this right here is the shutdown. This is, I took this picture. This is out of Buckeye, and you can see had a real nice tight seal. And everything is just a big math problem. We figured out, you know, how many turns per inch, how much of the wedge gate do we need to do in order to get that compression rate? So if whether you're at a 4-inch, a 6-inch, an 8-inch, or a 24-inch, as long as we follow the recipe, as long as you give us the correct data, then we can incorporate a valve in order to be a workable asset for you. There it is there, being placed into service, larger diameter, and we do require it before operating it to be poured in concrete on the large ones there. And you can see aging infrastructure, that's what they took out. So kind of in closing, how we kind of figure this thing out, we have a great program, we have a training and support program. You know, the biggest thing of what I wanted you guys to kind of understand today is that insertion valves is yes, it is new technology, but it's a technology that can really make your life a little easier. Basically avoid a water shutdown, be able to work smarter, not harder is my big thing. We have a whole program that we follow behind it, and also our authorized installers here in town, Pipeline Services and Tapmaster. They go ahead and abide by those, and they constantly get trained on how to do it. We've got the technical support and all that good stuff. Kind of follow our specifications, our data, and our product videos are all on our website. So kind of in review, no shutdown, made in the USA, the big thing for water conservation. The last part of this is the advantage is you're going to be able to, when you're using an insertion valve, you'll have that operational savings. You'll have the dollar savings because you're doing it a different way. You're not putting people out of service. You're not having a huge excavation point. You're providing system control where you didn't have one. You're saving water, and you're doing this in a safe and effective manner. I have 2 more videos. I don't know if they're going to play or not, but it was just kind of really shows the reason why we incorporate valves. I don't know if this one's going to go. This is just kind of an I'm not connecting the web. I'm not going to show that one. This right here is kind of like my last slide. Let me see if I can go through it here. This just kind of shows why people need insertion valves, especially under pressure. Try not to do it, but see if that'll play. Avoid bad days. This was probably in Texas. I don't know if some of you guys seen this or not, but I put it out there. It just shows the reason of why we need insertion valves and why incorporating a valve under pressure to avoid all of this is much needed and easy. But it also goes to a song of Had a Bad Day. So it's pretty interesting. There it is. So kind of in closing, insertion valves, feel free to take my card. If you've got any questions or anything like that, if you ever want me to present to some of your engineering team, just feel free to let me know. I'm all over the West Coast. We do these every day, and if you've ever want one done, just feel free to let me know. But it's a good way to kind of solve an old problem by a new technology. So thank you for learning about it, and thank you for letting me speak today. Thank you. Quick and easy.
Right. Real quick, excuse me. Thank you, Michael, for that presentation. We just got a few more things for you guys. Jason, would you like to take the mic? And then we'll let you guys go. I know you're trying to beat the traffic.
Okay, well, thanks everybody for coming.